Hi, I'm Brian Mullins, and this is Balls Out Physics, Episode 1, Planes Flying on a Spinning Ball. About 7 months ago, or well, 8 months ago, beginning of the year on New Year's Day, I went and saw Interstellar, and I thought it was awesome. And it got me to go back and read this book for probably about the third time in my life, What is Relativity? It was written in 1959. Really good book, very good explanation of relative motion. From planes moving across the earth with balls bouncing inside them all the way up to things traveling at the speed of light. It gives a really good explanation of Einstein's theories. And so, here I am, my head in the clouds, thinking about relativity and space travel and all this craziness. And I was, just bored one day, sitting on the couch, looking through YouTube videos, and a couple flat Earth conspiracy videos popped up in the that suggested videos to watch, and I'd seen those before, and I always had thought to myself, there's just no way, But I'm a very open-minded person, and I was in the mood to watch something different, so I said, what the heck, I'll watch one of these, thinking it would be good for a laugh. Well, about halfway into it, I wasn't really laughing. I was actually questioning a lot of things, and one of the biggest things that caught my attention was planes flying on a spinning Earth, trying to land on north and south runways. Because the Earth rotates from west to east, and things don't seem to line up based on the examples they were showing. This was all graphically, and so I started to look into this a lot. And what really surprised me at first is I'm a structural engineer, and I've taken a lot of physics courses in my life. And I started to look into the curvature of the Earth and the rotation and the speeds of Earth, and it kind of blew my mind that I've never really thought about how fast the Earth rotates or how much it actually curves. Here I am researching flat Earth theory, and I'm actually studying the curvature of Earth and the speed at which it rotates. I mean, there's some serious irony there. Our Earth, our model shows it spinning from west to east around an axis, which is represented by this little stick, and the circumference of the Earth at the equator, right here, is, the circumference of the Earth is 24,901 miles. So at the equator, since that's the farthest point from the axis of rotation, and there are 24 hours in a day, the speed of the Earth is 24,901 miles divided by 24 hours gives you 1,038 miles per hour. That's the instantaneous velocity at any point along the equator. I mean, that's what it has to be if everything we're told is true. So that's really fast. That's faster than the speed of sound, which is Mach 1, 761 miles per hour. So I never really thought about how fast that is. I always thought just kind of assumed it was moving really slow, and you don't really think about how much distance has to be covered in one day. But I also had never thought about or even calculated how much it actually curves. The general accepted value is 8 inches per mile, and I mean that's what it has to be based on the circumference, and that's 8 inches per mile, varying with the distance squared. Because if you're standing, or if you're on a point that's just above the surface of the Earth, or just on the surface of the Earth, and you look straight out away from you, across water, of course, because land has mountains and all kinds of things. But going across the surface of water, At the first mile, you would expect to see an 8-inch drop down to the curve. And at the second mile, because it's a curve curving down, it's continuously getting farther away from that horizontal line that you're driving, that you're sighting out away. The second mile is 8 inches times 2 miles squared, which is 32 inches. And then third mile is 8 inches times 3 miles squared, and if 3 miles squared is 9, it gives you 72 inches. It starts to drop off pretty quick. And so I'd found that the flat earth community had created this. Someone out there did this. This is a curvature chart. The flat earthers are making a curvature chart. And they're showing how much curvature would have to be, we would have to see in all directions, because it's a sphere, anywhere on Earth. And this was drawn in AutoCAD, and since I'm an engineer, I have access to AutoCAD. The first thing I did is I went and drew a circle with a radius of 3,959 miles, which is the accepted radius of our Earth. I converted that to feet, which comes out to over 20 million feet, and started plotting points and finding that this is very accurate. This is exactly what you get. So I'm starting to wrap my head around how much curvature there should be, and that's quite a bit. And it's kind of hard to find it. So anyway, one of the first things I did is I set up a problem about the spinning planes. It was a physics problem. I'd studied relativity. I figured I could do this. The idea of this problem is that we are an observer, a stationary observer, looking at Earth, watching a plane fly. And this is based on a direct flight I took in college from JAX to LAX. The two airports are about 2,000 miles away from each other. And I flew there and then flew back, and I like doing the problem going back because it's more interesting that way. Because we're rotating with the Earth, and also a lot of some flat earthers out there have said things like, if the Earth is rotating 1,000 miles per hour at the equator, planes can't fly that fast, so they can't catch up to it, and that's not really true, because if the plane's already rotating with the Earth when it takes off, the speed it gains in the air is added to the initial speed it already had. So that's not true. But there is a problem here, and that's what I want to get into. So these two airports are 2,000, here's my dimension line here. They're 2,000 miles apart roughly. And we're just going to say they're 2,000 miles apart in order to keep this simple. Okay? And they're also, they're not at the equator. They're north of the equator. A little over 2,000 miles, both of them. Jacksonville's over here in Florida, and LAX is over here, California. LAX is about 250 miles north. I think 250 miles north of JAX in Jacksonville. But we're going to say that they're at the same latitude, just to keep it easy, to keep the problem easy. And so, as I was showing you on the ball, as you move up away from the equator, the diameter of the Earth around the center axis decreases, so your velocity decreases. You can calculate this, and I played around with some numbers, and I got between 850 and 900 miles an hour for both airports. So I just said let's just use 900, just to keep it easy. It's a hypothetical problem, but it is based on reality. So the reality we're all taught to believe. So here we are. We're going to fly back to JAX. Sitting on the airport in LAX, we're going 900 miles an hour east. The Earth is moving that fast, but we can't feel it because everything's stuck to it, right? So we're told. So the plane takes off and gets up to its cruising altitude, whatever that is for the day, 30,000, 33,000 feet, whatever they're going to fly at. And it gets up to a cruising speed of, let's say, the velocity of the plane, VP, equals 600 miles per hour. Now, since it was already moving, the velocity of the plane relative to Earth, which we'll call VPE, is now 600 plus 900 miles an hour, gives us 1,500 miles per hour. This thing's really moving. Okay, but it's relative velocity, so it only seems like 600 miles per hour to us on the plane, right? That's the theory. So everything makes sense. We're moving fast, 600 miles per hour faster than the Earth is spinning, so we're moving towards Jacksonville. But here's where we run into a problem. Let's say there's a north-south runway in Jacksonville. Now Jacksonville's runways are actually orientated kind of 45 degrees northwest and northeast, but north-south runways do exist. You can go look on Google Earth, you'll find them. They're all over the place. And of course, LAX's runways all point east-west, and they're right on the water, or right on the ocean. So we get up here to this point, right before they make the turn, the plane slows down. Okay, this is where the problem comes in. Planes cannot stop flying before they make a turn. They can't go to zero, and going to zero would bring you back to 900 miles per hour that you started at. But you can't go to zero because a plane has to keep flying forward to have uplift on the wings and keep itself in the air. Duh. So it's going to slow down before it makes the turn, but it's not going to zero. So let's say it slows down to 300 miles per hour. And then it also, that's the speed it slows down to before it makes this 90-degree turn, or this right angle turn. So here, the plane, right before it makes the turn, is traveling at VP prime equals 300 miles per hour. VP prime is just the new speed, okay, or the new velocity in this direction. But it's also got its relative velocity to Earth, which would be VPE prime, is now 300 from 1500 is 1200 miles per hour. So now, as this plane goes through the turn, when it gets here, say the midpoint of the turn, it's got a vector of 300 miles per hour, which is its airspeed, this VP prime, in this direction. But it also still has this velocity of VPE prime right up here, 1200 miles per hour. It doesn't lose that velocity. It can't, because the Earth is spinning under it. And it had that initial speed when it took off. The only way you can get rid of that is if you make the Earth stop spinning. So, when you get down here and you're trying to line up with the runway, you're going 300 miles per hour towards it. Make that look a little better. You still got VP prime here, but you also have VPE prime. Well, there's a real problem there, because the airport, the ground over here, is moving, you can see that, at 900 miles per hour. Except the velocity of the Earth is the same at both airports. But the plane is moving to the east still at 1200 miles per hour. The plane is moving faster than the runway. They can't line up. What you actually get, if you draw this point over here, actually let's erase this and do it right here where we started. What you would actually end up with is a path that looks like this. More of a linear path, because the plane, if this point represents the plane has a vector this way and another much larger vector this way. So you're getting something like that. The plane is actually sliding sideways through the air. That doesn't make sense. I mean, it's kind of what's going on. This question, of course, people say, well, the atmosphere, this is what I thought too initially, the atmosphere is moving with the Earth. So, since the atmosphere is moving with the Earth, it's like a fluid that you're traveling through, so it doesn't matter that your initial speed was 900 miles per hour, and then you have a relative speed, and that doesn't work. When you really start to think about it, it doesn't work. The best example I got from another engineer I showed this problem to was, he said, what about a fly on a train? The train, the air in the train is moving with the train, and the fly can buzz all around inside the train. You've probably seen bugs in a vehicle before of some sort. The fly is unaffected by the movement of the train. Well, first of all, a fly can hover, which a plane can't do, and also the air in the train is contained within the shell of the train. Earth does not have a shell that, at least so we're told, that contains all the air. The space shuttles and rockets and everything flies through it. They leave the Earth. What's supposed to hold our atmosphere to our Earth is gravity. So we're told, air actually still has a mass, and so gravity pulls. Anything with mass exerts, as we're told, anything with mass exerts a force on anything else with mass, and they attract each other. I'll get into that in another episode, because that's also a big issue I'm finding. But so the atmosphere, spinning with the Earth, wind blows in all different directions. It's not constantly blowing from west to east, because if it was moving with the Earth, it would be blowing from west to east. And that wouldn't help us at all, because the plane is also going from west to east, so if anything, the atmosphere is just pushing it along. It's not helping slow it down. If you reverse the problem and go the other way and flip the runways around, which is what I initially did, you end up with the plane going 300 miles per hour too slow. And of course, if the atmosphere is going from west to east, then maybe you could say that the atmosphere pushes the plane back up to that velocity. But Newton's first law says that an object in motion stays in motion unless acted upon by an outside force. So an object in motion relative to another object in motion stays in motion relative to that object unless acted upon by an outside force. It has to. The atmosphere doesn't answer the question. And the other problem with the atmosphere is air gets thinner as you get farther away from the Earth. So the gravitational pull on the air as you get higher and higher is less. So by conservation of angular momentum, air at higher altitudes would have to be spinning slower. And this is where the actual concept of dark matter comes from in galaxies, because stars at the outer edges are spinning at the same speed as stars in the inner ring of the galaxies, and so we say there's more mass there to make up for this. And that's another thing I'll cover in a coming episode. But there's no real answer for this. So I started thinking about this. I'm trying to visualize this, because we never do problems like this. In my engineering classes in college, we used to break down, we derive equations, calculus. We use calculus to break down equations that somebody else had already derived before, and I always thought it was annoying because it always comes down to a simple algebraic expression. Everything in our world becomes very simple. It's kind of amazing, but everything breaks down to a simple algebraic expression. We go through all this proof to back check what these guys had done, but never did we back check our theory of living on a spinning ball, ever. We don't do these problems. Why? Why don't we talk about the curvature? Why don't we talk about the velocity? I went back to school and took astronomy in 2013, and we kind of talked about this, but not in depth like this. And then the other thing I started to think about is, I live in Central Florida. I heard a sonic boom one time from supposedly the space shuttle landing. Rattled my windows and doors. It woke me up, scared the crap out of me. It was pretty awesome, actually, at the time. The landing strip for the runway at Cape Canaveral is north-south. The north end actually points a little bit to the west, this way. Actually, west is actually this way. But it's mostly north-south. And I also have seen space shuttles take off from the beach. I accidentally saw one. I just happened to walk out on the beach up in Jacksonville one time and saw one take off. And I saw it go out over the water, going to the east, which would actually be this way. Going out over the water to the east. And then it disappeared from my sight. I thought it went out into space. So it's rotating with relative to the rotation of Earth. Definitely. And when it gets up into space, it's still going to have those components. It's adjusting with we're told it adjusts its movement in space with air jets. Spraying mass out into nothingness, which I'm also going to do another episode on, because that doesn't make sense either. But we'll get into that too. So now this shuttle is going to re-enter the Earth's atmosphere, traveling at thousands of miles per hour when it comes back in, and it's supposed to come back in gliding. It comes through the atmosphere, and you've seen all those videos where the fuselage heats up, and it's slowing down, of course, as it's coming into our atmosphere. But if this thing is coming in at thousands of miles an hour, and trying to come in from either the north or the south end of that runway, and it definitely has components of velocity to the east or west, and that runway is spinning somewhere between 850 and 900 miles per hour to the east. This is insane. The little jets that shoot to the side and the shuttle aren't going to do anything in our atmosphere. This is insane. It doesn't work. Really, try to think about this. Try to wrap your head around an Earth spinning. In all the movies we see of space, the science fiction movies and everything, whenever like a ship is coming up on a planet, the planets always seem to be stationary, because if they were actually rotating at the speeds they would have to be rotating for the length of their days, whether it's Earth or another fictional planet in a movie, it would probably hurt our heads to have to see the ships and things rotating like that. So for Hollywood, and then to make things easier, we see it stationary. It appears stationary. Of course, you could say it's moving too slow, but it's actually moving pretty fast. So, Earth is, at least. So anyway, here's the spinning ball problem, but we also still have the curvature problem here. We're flying a great distance, 2,000 miles. And based on that curvature chart I showed you earlier, there's a lot of curvature that this plane has to fly over. So, in the architecture and engineering world, looking down on something is called a plan view. So we call this a plan view of Earth. And we cut sections through our plan views to look at a section through a building or anything we're designing. So what if we cut a section through the Earth here? This is typically what a section cut line looks like, something like this. Okay, so we're going to cut a section and turn our view, up, looking into the plan view. Okay, so let's draw that. Still 2,000 miles apart from here to here. And say this is LAX over here, and this is JAX over here. Both airports are roughly at sea level. I mean, LAX is right on the water, and JAX is a little bit inland, but I mean, Florida's flat, so it's basically at sea level. So we've got this curve of the Earth, the amount of curvature that we would see over 2,000 miles, and here is our datum line, which is sea level. Okay, so this is LAX, this is JAX. Okay, so this distance here, get something, use a different color for this. This distance here to the curve would be based on 1,000 miles an hour, 1,000 miles of distance. Excuse me. I mean, this is rough because where do we actually measure? Do we measure across the curve, or do we measure the distance between the 2 points? Miles are linear measurements, but we'll just ignore that and just keep it simple and say 1,000 miles. Now you take the curvature chart, you look on here, see if you can see 1,000 miles. 1,000 miles. The height of your curve at 1,000 miles should be roughly 128.4 miles. All right, so this distance here is 128.4 miles. Okay, our plane takes off, heading this way, I guess, because it has to follow the curve, and it gets up to about 30,000 feet, 33,000 feet. That's 5 miles. That's a mile is 1 mile is equal to 5,280 feet. So now you're up here somewhere, and you're trying to fly over here, like this, I guess. I mean, you can't fly through the Earth like that, so you still have to follow the curve, obviously. Well, this plane is flying along and follows this curve, right? The Earth is constantly curving, so the plane constantly has to be following the curve. Well, that's a problem because when the rudders on a plane are straight, the flaps or rudders, whatever you want to call them, they're called rudders because it's just like a boat moving through water. Air is a fluid, really, and so when you turn a rudder on a boat, it controls the direction of the boat. Just the same thing in the air. When a plane turns its rudders on the wings or on the tail, it affects its motion through the fluid, but this is the atmosphere that's flying through, and it controls its orientation and where it's going. So to follow this curve, the plane would constantly have to nose down. The pilot would constantly have to nose the plane down if that's how a plane flies. When I first thought about this, I'm like, that's crazy. The Earth is constantly curving, so it constantly has to nose down to follow it. So I got on the internet and started looking up explanations for this. People have asked this question before, obviously, and the general accepted explanation for this is that gravity does it. It's basically like it's going into orbit, and because you have that force, you have this force of gravity on the plane pulling towards the center of the Earth, it makes you follow this orbital path. It's like a ball on a string spinning it around. The force in the string pulling it towards the center makes it actually rotate around. I mean, that's where the theory of all of our orbits in space comes from, is that force pulling towards the center of mass. All right. But see, there's a problem with that because the rudders on the plane are not the rudders, the rudders, elevators, whatever you want to call them, they're straight, but we're following a curve. Okay, so even though the pilot's holding the controls or autopilot or whatever, I mean, they're making little adjustments here and there, but I mean, basically, you fly up and you level off. You feel that when you fly on a plane if you've ever flown on a plane before. So, what if you said the gravity is the explanation for that. I said, okay. I started thinking about it. That makes sense. I thought about things orbiting Earth, but what if the pilot, let's draw a plane again, say up here somewhere. What if the pilot decides he doesn't want to follow the curvature of the Earth for some reason, and he wants to follow a point, a line that is tangent to the Earth, like this, a straight line. So, the pilot wants to follow that line and not fly, he kind of wants to fly up relative to the curve, I guess, or down, depending on which way you're looking at it. But, so now he's got this force of gravity that's trying to make the plane follow the curvature of Earth, based on the accepted explanation for what I was talking about before. So, if you want to fly in a line that's tangent to a point on the Earth, then you have to fight that force of gravity that's trying to make you follow the curve. So now it's the same problem in reverse. Now you constantly have to pull up on the controls or nose the plane up to fly in a straight line. With the rudders, you're cutting through the air, but you're flying in a straight line with the rudders actually angled like this to make the plane fly straight. That doesn't make any sense. This doesn't work. That's not an explanation. Gravity is not doing this. Where's this curvature? And when you fly in a plane, you'll notice when you look out the window, the horizon, of course, looks flat, and we're told that the Earth is too big and we can't see it, and it's also at eye level. If there's really a curve, there should be a drop. Now this one, people argue about this one. It's a big argument in the flat Earth, round Earth community, but it's becoming a huge debate on the internet. More and more people are waking up to this. It's pretty amazing, and what we're not taught in school is. In the late 1800s, there was a raging debate going on between, flat earthers and globulists, as they were called. People still believed that the Earth was flat. Well, Columbus didn't sail to America and prove. Everybody just started believing the Earth was a ball. A lot of people didn't believe it, and there's actually I've read some testimonies from civil engineers in the 1800s that just say it's ridiculous. When they're talking about laying train track and all kinds of things. So I'm at a loss here. I don't know what to think. I'm kind of thinking it's flat and stationary. I've gone to Lake Apopka and I've taken my telescope there, and on the south end of the lake, Lake Apopka is one of the biggest lakes in Florida. I think it's the second biggest. On the south end of the lake with my telescope sitting 3 feet above the shore, I can see the North Shore 8 miles away. Well, based on the curvature chart, there should be, what is that? Based on 8 miles, I should have a 43-foot drop from one side to the other. I shouldn't be able to see the shore. There should be a curve of water in my way. You can't see it on a rough day when the waves are in the way, but on a calm day, you can. That doesn't make sense. I should not be able to see that. So, I don't know what's going on here, I've had my world turned upside down or right side up by this. I've spent a lot of time researching this, a good 7 months, and I've seen a lot of different things. There's a lot of topics to talk about, but this is the one I thought I'd start with. So, you guys out there, you can leave comments, call me crazy if you want to, but you got to give me an explanation for this if you're going to call me crazy, and help me out here. I'd love to go back to believing that I live on a spinning ball, and this isn't some massive conspiracy, and we all haven't been duped. But human beings are very easy to fool. And it's actually much easier to fool a human being than to convince a human being that they have been fooled. We come into this world, we don't know where we come from, we don't even know how our thought process actually work. We don't know how we're able to simultaneously create thoughts and perceive them at the same time. We still can't explain that. So what do we really even know? Anyway, that's getting off topic. This is episode 1. We'll be getting into more. I'll have many more episodes after this, hopefully. So, until next time, peace. Hi, I'm Brian Mullins, and this is Balls Out Physics, episode 1.1, A Spinning Atmosphere. Now, I just noticed the other day that my very first video, Balls Out Physics, episode 1, Planes Flying on a Spinning Ball, was reposted on another channel on November 6th, and since then it's gained over 250,000 views.
Now that's surprising. I don't know how that works, but it's awesome because it gets people thinking about this problem. When I first started looking into the idea of a rotating Earth and really thinking about that and applying it to the everyday world I see, one of the first things I thought about were planes flying above a spinning Earth, and I talked about that in that video. And I couldn't really find, actually I couldn't find any type of relativity problem that used planes and a moving Earth. Now there's tons of relativity problems out there showing trains and cars and other things that are moving on a surface that is assumed to not be moving, but there's nothing that takes into account, at least since I haven't looked since then, that accounts for an Earth moving with the planes. Now if you scroll through the comments on that video, I posted a link to where my video has been reposted, people saying the same thing that even I said, is of course the air slows the plane down, because my argument was an object in motion stays in motion unless acted upon by an outside force. So what's slowing the planes down? Because I said the atmosphere, I didn't make the statement, which I should have done, about my assumption of an atmosphere spinning with the Earth. How can that be? And so I implied in the video that why aren't the planes going into orbit? Okay, now we know in this reality that planes slow down because of air resistance. That's obvious. The whole point of that episode was to get people thinking about it so we can try to explain this. And so this video is about the concept of a spinning atmosphere and why I have a lot of trouble with it, and really why I ignored the spinning atmosphere in my very first episode. So let's say we're looking down on the North Pole of the globe Earth, and the Earth is rotating, spinning, or I should say rotating. People have given me some criticism for I should say rotating instead of spinning, because they said it's being deceptive to say spinning, but I mean spinning, rotating, I really think it's the same thing. So anyway, Earth is rotating, right? And so let's say we're going to freeze the Earth at that moment. Freeze the Earth with the atmosphere around it, assuming that the atmosphere is rotating with the Earth. And that's what I have drawn on the board here. Okay? So here's the Earth down here. Alright, and let's say that this line right here is the equator. When you're looking down on it, the equator is right here. Okay, so we're just going to say this line is the equator, and then this is the edge of the atmosphere up here, and then there's space out here. Now this is obviously not the scale, this is just conceptual. Okay, and so at the equator, the circumference of the Earth is roughly 25,000 miles. And so to figure out the instantaneous velocity of the Earth as it spins around its axis on the equator, you divide the circumference by the time it takes to make one revolution, which is 24 hours. And when you do that, you get roughly 1,038 miles per hour. Okay? And so we assume right here that this is the Earth rotating at 1,038 miles per hour. And I said in the video, and people have said in the comments, that you can just say that that's zero. Okay? And so what I want to do is look at this atmosphere and look at 3 points and 3 elevations, okay? A, B, and C, and assume that we're looking at just 1 cubic foot of air, okay? Just to get our minds around this volume of air that's frozen in time right now, okay? So all of it's moving, all the air is moving with the Earth in such a way that it appears relatively stationary. You know, we go outside, wind blows and moves around, but it's all moving with the Earth, and that's what slows the plane down, because the atmosphere moves with the Earth, okay? So point A, point B, and point C, all moving with the Earth. I mean, they could be blowing this way, they could be blowing down at this moment, but since we froze them, we know that it's all moving with the Earth and not getting left behind, right? That's the assumption. And so we will say at this moment we expect all of these points of air to make one complete revolution and come back to the same spot in 24 hours, right? Because the atmosphere moves with the Earth. The atmosphere never gets left behind. So right off the bat, since we know the velocity is equal to distance divided by time, we can say that VA, the velocity of point A, is greater than the velocity of point B, which is greater than the velocity of point C. Because point A has a longer distance to travel in 24 hours than point B, and point B has a longer distance than C, because the circumference of their path is greater, right? So I've got A up here at the edge of the atmosphere, space up here, B right here around 6 miles where planes fly, and C near the surface of the Earth, okay? And so this rotation here, the theory is that the Earth is rotating about its axis because of the Big Bang. When you really think about it, there was this Big Bang, and everything exploded out into space, planetary systems formed, galaxies, all that stuff formed, and this rotation is what is left over from that explosion. That's leftover energy from that explosion of the creation, which created everything, right? And so everything's just been moving for billions of years, and there's no friction between space and the atmosphere, right? Because there's nothing in space. So an object in motion stays in motion unless acted upon by an outside force, right? But that's kind of strange when you think about that air at higher elevations has to be moving faster to keep up with the ground below it. Because air moves up and down, right? Hot air rises, as we know, and cool air sinks, right? So how does the air speed up? When it's heated, it rises, but then it has to start moving faster. Now, even if it's only a little bit faster, the difference in these velocities, if you calculate them, isn't much, but they do have to be greater, or they will start to get left behind. So, how that is explained, I don't know. I haven't really found anything to talk about how the air has to be moving faster. But another thing to think about is, air isn't stationary like we're assuming in this problem, right? It blows, it moves all over the place, and down here at the surface, air goes up and down over valleys, and air actually speeds up as it goes up and as it goes over the top of a hill. It speeds up, it slows down, runs into mountains, goes through trees. There's things flying around in the air, different pressures. All kinds of stuff is happening internally as it all moves with the atmosphere. Now, I would think that eventually something's going to have to give it a nudge to keep it moving with the Earth, so to say. The energy would be lost, okay? But not to mention that, there are things that enter our atmosphere. There's meteors, all kinds of stuff is constantly is supposed to be entering the atmosphere from outer space. So that is pushing back on the atmosphere and wanting to slow it down. And so the common explanation for how the atmosphere keeps up with the surface of the Earth is by friction between the air at the surface. Let me use a red marker for this. There's friction here pushing back on this cubic foot of air down here that's at the surface. And then that's transferred through internal friction, for internal shear forces within the fluid, because air is essentially a fluid, okay? It has viscosity, and so these internal shear forces are transferred all the way up throughout the layers of air, right? Just the air pushing against itself, the friction carries that force all the way up to keep the atmosphere moving with the Earth, right? Well, the problem I have with the thing that doesn't make sense to me, and this is why a lot of this is why I ignored it in the first episode, though I didn't explain it, is when you create friction, you create heat. You rub our hands together. It's actually kind of cool here today. Rub my hands together to warm them up. That creates heat. Heat is essentially kinetic energy. And so when something creates heat on the Earth, or when the Earth is heated by the sun, where does that heat go? Well, if you watch Balls Out Physics episode 4.1, I talked about how the accepted explanation for how things don't just get hotter and hotter and hotter is that it radiates out into space, right? So heat from the Earth radiates out into space, into infinite space, and is lost forever. So this process right here, this friction process, the shear force process, creates heat, and that heat is escaping. Therefore, this whole system would be losing energy, wouldn't it? And so we say that heat is really kinetic energy, and kinetic energy is equal to 1/2 mass times velocity squared, right? And so this kinetic energy, I assume, is going down. The kinetic energy of the atmosphere is going down because it's losing heat. And since I hope we're not losing mass to infinite space, not losing our air, that leaves only velocity to go down. So not only does the speed of the air relative to the surface of the Earth have to increase as you go up in elevation, because the path it has to travel, the length of the path, the circumference, increases. We also have this problem with losing energy. I don't understand how this could work. And that's one thing I've been thinking about. I hadn't really come up with a way to explain it until making this video. So how does this atmosphere keep up with the Earth? And this is why in the very first episode I really was saying, how do planes not go into orbit? Because how does the atmosphere, in a sense, keep up with the Earth? I probably should have made this video first. So that's how I feel about this. Please keep the discussion going. I'm going to post a comment on the repost of my first video saying that I made another video to keep this discussion going, because that's what this is all about. It's just talking about this world. And if you agree with my analysis, or you don't, or you just want to keep the discussion going, please go to the video. I posted a link in the description below, and like my comment so it'll get bumped to the top so people can see this video, and then we can keep this going to figure out what's going on here. Because really this increase in velocity that you have to keep up with the Earth doesn't make sense. And then the heat loss to me. Another thing a lot of people have said is you can set the velocity of the Earth equal to 0, right? Because of relativity, we just say that the Earth isn't moving for the plane problem, right? But if VC, right at the ground surface is roughly 0. I mean, it is a little bit above the surface, so it would have to be slightly faster than 0, because its path is slightly longer if you go to the center of a foot. That's just getting too far into it, though. So if we say VC is 0, then VB and VA both have to be greater than 0 to keep up with the Earth, or they'll get left behind in 24 hours. So how does it all work? How do these things blow and move all over the place but still keep up with an Earth that's rotating? How does that work? There's just too much going on. It doesn't really make sense for all this movement to be happening, but us to go outside and experience this relatively stationary air that we experience every day. So that's my thoughts on this. Please keep the discussion going, and until next time, peace. Hi, I'm Brian Mullins, and this is Balls Out Physics, episode 1.2, Flying Over the North Pole. I gotta thank Deep Inside the Rabbit Hole for pointing this out, because it really helped me develop a south-north-north-south flight problem, where I think the issue that I was trying to explain in episode 1.0 is really shown. And so, what I have here is a view of the Earth looking down on the North Pole, kind of like I was talking about in episode 1.1, looking down on the North Pole like this. What I have is Quito, Ecuador here, and Singapore over here. And so if you look at this on the globe right here, Quito is right here in Ecuador. We're going to say it's right at the equator. It's a little south. Okay. We're going to take a flight from Quito over the North Pole to Singapore over here by my thumb. Okay. Now, Singapore is at 104 degrees east of the prime meridian, and Quito is about 78 degrees west. And so that's 182 degrees between them. But I'm showing a straight line here. We're just going to assume that they're 180 degrees away from each other. And the runway at Quito actually faces almost due north. So we can say that the pilot's going to start off and fly directly at the North Pole. Okay? And so when a plane is sitting on the runway, it's moving with the Earth, right? If in the heliocentric model, if the Earth is rotating about its axis, we're all moving. I'm moving, you're moving, we're all moving at different speeds based on how far we are from the equator. Well, that's the way I figure it out, at least. And so at the equator, I'm going to say here that the circumference is 25,000 miles. You can say it's a little bit less, but we're just going to keep it simple and say 25,000 miles. And we're going to say that the Earth makes one rotation in 24 hours. Now, you could argue that in a heliocentric model, the Earth makes one complete rotation in a sidereal day, which is 23 hours and 96 minutes, but that's a topic for another time, and it's only 4 minutes difference. And we're also going to say, to keep things simple, that the flight from Quito to Singapore takes 24 hours. And we're also going to say that that distance is 1/2 of the circumference of the sphere. We're assuming a perfect sphere here. And so that's 12,500 miles. And if it takes 24 hours, that gives you an average flight speed of 521 miles per hour, which is very possible. And flying 24 hours is also very possible. I looked it up. The longest flight ever was for 4 days. They're probably refueled in the air. But a plane could be outfitted to fly from Quito to Singapore. So now, when the plane is sitting on the runway in Quito, facing north, here on Quito, the Earth is rotating, right? And so, if the Earth makes one rotation in 24 hours, 25,000 mile circumference divided by 24 hours gives you speed and instantaneous velocity on the Earth of 1,042 at the equator. At the equator gives you an instantaneous velocity of 1,042 miles per hour. Now you notice for the plane, I wrote speed instead of velocity because in physics, speed is just a rate, whereas velocity is a rate and a direction, or having a vector. And I'll get back to that in a minute why I wrote speed there. So the plane is sitting in Quito, use a marker here to represent the plane, facing due north towards the North Pole, and it takes off and leaves the runway. And as the plane begins to fly towards the North Pole, well, the speed of the Earth below the plane would change, right? Because since velocity is distance divided by time, or speed is distance divided by time, whatever you want to look at it, the circumference of the Earth around the axis of rotation decreases as you fly north, right? Because the Earth is curved. And so I just did this by drawing it in CAD. When the plane gets to New York City, or at the same latitude as New York City, around there, the speed of the Earth has dropped to 800 miles per hour. But the plane should still be moving at VE, the velocity at the equator, with 1,042 miles per hour, right? Because on the runway, it was moving 1,042 miles per hour. What slowed it down? That's its moving. If you go back to episode 1.1, I was asking the question, how does the atmosphere spin perfectly with the Earth? Let's say it does. If that's true, does it create a suction force on the plane to slow it down? How does the plane match the speed of the Earth? How would it stay in a straight line? Would the pilot have to be constantly turning to the left a little bit to stay pointed at the North Pole, since the Earth is slowing down under it? And you see, when you get up here to 68.5 degrees north, the speed actually reduces to 400 miles per hour. How would this work? And I mean, this just isn't in this theoretical problem here. Anytime a plane is flying south or north, this problem would exist. That's whatever speed they started out on the runway, they would still have in the air. Now, if they're flying east-west, you could argue that the atmosphere slows the plane down, or as necessary, as was the response to my first video. But in this case, the plane takes off and the Earth is slowing down below it. I think it would actually go like this, maybe, or the pilot would have to keep adjusting. And of course, there's also what I mentioned in episode 1.0 of the plane having to constantly nose down to follow the curvature of the Earth. Now, the explanation for that was that gravity does that. Okay, gravity takes care of that, so the pilot doesn't have to do that. Okay, so if we were going to look at the Earth this way, at this flight, say we're going to look at it in this direction as it's flying over the North Pole, we'd see something like this. Okay, so here's the Earth, North Pole here, this is your axis of rotation, and here's the plane traveling in its path. Now gravity is what keeps it following the curvature of the Earth, right? Well, this plane, what's going to keep it following this axis of rotation? Gravity doesn't pull in two directions at one time, does it? Does it pull towards the axis of rotation as well? How's that going to work? And so the plane, as it's moving, flying over the North Pole, is going to encounter the Earth actually changing directions below it. Because here the Earth is moving this way, and as the plane crosses the North Pole, now the Earth is going the other way. This is what Deep Inside the Rabbit Hole pointed out in a comment on my last video. And so you have to remember, though, that the Earth is also moving, right? So as it flies from Quito to 68.5 degrees, that's about 3/8 of the way through the flight. You know, it takes 12 hours to get to the North Pole if we're assuming perfect 24 hours, roughly. The Earth has moved, right? So Quito is now over here after 9 hours, still moving with the velocity vector, VE, at the equator. And Singapore is over here after 9 hours. So where's the plane in all this? Is it still following this line, even though it's moving faster than the Earth below it? Because again, an object in motion stays in motion unless acted upon by an excited force. So what slows the plane down to keep it with the Earth? It can't be gravity this time, because gravity, as I said, is already taking care of nosing down. So as the pilot, if gravity's not doing that, as a pilot constantly nosing down and turning to the left a little bit, I mean, I've played flight simulators and know enough about flying. I've never flown a plane to say I don't think they have to do that when they're flying north or south, because this problem would happen when flying south, as the Earth would be speeding up under the plane. So if you took off from a location to the north. So I don't really see how this works, and I think there's still a problem here. So thoughts on this? When relativity problems are done, they're always done with something moving in a straight line, linear motion, not circular motion. To keep the plane moving around this axis of rotation, you would need a centripetal force to resist the centrifugal force that makes it want to fly off the circle, right? It makes it want to move in a straight line. When you spin around one of those merry-go-rounds in a playground, if you ever did this as a kid, we used to get a bunch of kids on it. One person would spin it as fast as they could, and everybody lets go, and they fly off in a straight line, a line that's somewhat tangent to the circular motion that you're moving in. So why wouldn't this happen here? Why wouldn't the same thing happen here without that force, without a force pulling towards that axis of rotation? So just my thoughts on this, more problems to think about. Again, why don't we do problems like this in physics to explain how this all works on an Earth that's rotating around its axis and then revolving around the sun and all that. So my thoughts, till next time, peace.
Hi, I'm Brian Mullins, and this is Balls Out Physics, Episode 2, The Gravitational Constant. Before I begin, I really want to thank everybody who commented on the first episode. The positive feedback was fantastic. I had no idea the video would be so well received. Thank you all for taking the time to watch it and really think about it. And even in some of the negative comments, there were some very good questions asked, and I would definitely like to revisit the plane problem after a few episodes. But there's some topics I'd like to cover first, because I think it'll better explain the plane problem as we go along. And so the other thing I want to say is that I'm not claiming to be right about all this. You know, when I first discovered flat Earth theory, I thought I could debunk it right away. You know, but the problem was I couldn't. I realized that there are some very good points being brought up by the flat Earth community, and that's why I started this series, because I'm really asking for help here. I can't explain these things, and you know, I've got a pretty strong physics background. I took 2 physics courses in high school and then a bunch in college to get my degree, and maybe I'm missing something, maybe I'm not. But one of my favorite sayings in the engineering world is, you learn 10 times more from your mistakes than you do from your success. This is what we always tell rookie engineers. This is what they told me. Don't worry about making mistakes. Don't worry about being wrong. Because when you are wrong or you do make a mistake, you want to find out why. And on the way to finding out why, you learn a ton. So never be afraid to be wrong, because you can learn from it. And no one on this earth who has ever lived on this earth has ever been right all the time. All the time. It's never going to happen, and it's never happened. So accept it. Learn from it. So anyway, this episode is mainly about gravity, but it's about the gravitational constant in the gravity equation. However, to get there, we need to start with some basic physics. And so I've set up a problem here with the Earth, represented by this blue ball, and me or any other man or woman standing on the Earth, and how we determine the weight of that person, okay? Or the force of gravity acting on that person. Weight and the force of gravity are actually the same, or at least that's the accepted belief in physics. You know, weight is actually caused by the force of gravity of the Earth pulling down on the object, in this case, the person. And so the bread and butter physics equation up here, one of the first equations you learn in Physics 1 is force is equal to mass times acceleration. This is what Newton based all of his three laws of motion on. And since his boy Copernicus, 150 years prior, had come up with the solar system, he knew that he needed to come up with an equation that would not only work on Earth, but would work throughout the universe. Okay? And so what this equation says is that the force acting on an object is equal to the mass of that object multiplied by the acceleration that the object is experiencing. Okay? And mass is defined as the amount of matter in an object. And in Physics 1, they hammer into your head that mass is the same throughout the universe. Only weight changes because the gravity on each planet can change. You know, the gravity on the moon is less than it is on Earth. It's supposed to be about 1/6 of what it is on Earth. And so I was taking physics, and I had just taken chemistry, or I was taking it at the same time, I can't remember, but I immediately thought about the fact in the lab we were weighing things in terms of grams. And in the metric system, grams and kilograms are actually units of mass. But to determine mass, we actually weigh it, or weigh an object, and we say this is how massive it is. And so I thought to myself, well, if that's the case, if I took that same scale up to the moon, it would definitely give me a different reading because the force of gravity is less, and that's what's pulling the scale down, right? So how can that be? How can mass be the same throughout the universe? Does that mean we would have to calibrate our scales to work on the moon so that they show the same mass that we get on the Earth? Or do we use a conversion factor instead? Or how does that work? Does that mean that just all mass in the universe is actually defined on Earth? I don't know. I never really got that, but at the time I had been in school for a long time. I was 18 years old and I was ready to get out and go make some money, so I didn't really ask too many questions. However, I always questioned that and I always thought about it, and I've talked about this with some other people, and there are a lot of people that say, yeah, that doesn't really make a whole lot of sense. But it's accepted in the physics world. So anyway, that's mass. Okay? The mass of an object, the amount of matter in an object. The acceleration is defined as any change in velocity. Okay? So velocity can be measured in miles per hour, as I did show in the first problem, or kilometers per hour, kilometers per second, meters per second, whatever. That's the rate of velocity. However, acceleration is defined as any change in velocity. So in this example, if I'm standing right here on this Earth, okay, I have a velocity. I'm moving with the Earth. As you remember in the first problem, we said I'm in Central Florida. My velocity is probably around 900 miles per hour, maybe a little less, somewhere between 850 and 900 miles per hour. Okay, but since the Earth, I'm supposed to be standing on an Earth that is rotating. This direction of that velocity is constantly changing. Okay, so when I get over here, you know, this is exaggerated obviously, but now my velocity is pointing this way. So, even though I'm standing at rest, because of this theory, I'm constantly accelerating. because the direction of my velocity is constantly changing. And this will be better explained in the next episode when we talk about centrifugal force. So anyway, since weight and mass are different, weight is actually considered to be a force. This force of gravity, we have weight over here and weight here, weight is equal to the force of gravity pulling me down. Okay? So this equation can be rewritten, F equals ma can be written as weight is equal to mass times little g here. And little g is considered the acceleration due to gravity, or the acceleration at which things fall towards Earth. Now, I posted a link in the description to a trailer for the BBC series episode 4, Human Universe, in which Professor Brian Cox from the UK, travels to the Glenn Research Center in Cleveland, Ohio, to do an experiment with NASA's vacuum chamber. And in the experiment, they drop a clump of feathers and a bowling ball. And the first time they drop it when there's air in the chamber, the bowling ball obviously falls a lot faster than the clump of feathers. But when they remove all of the air from the vacuum chamber, both the feathers and the bowling ball fall at exactly the same rate. So what this little g says is that all objects accelerate towards Earth at the same rate unless there is some type of fluid preventing them from falling at that rate. And so the more dense something is, the faster it'll fall through the air. The less dense, the slower. It's just like in water. Something heavier or more dense, more massive, will sink faster than something that's less massive or less dense. And if the density is actually less than water, it'll float. And the same with our air. That's how hot air balloons work. Or blimps with helium inside them, or balloons. That's why they float, because their density is less than that of air. But when you get rid of air or any fluid, everything falls at the same rate. And that's a really great episode. I highly recommend you watch it. It's very interesting to see. Okay, so that's weight. Okay? And weight or force in the metric system is measured in newtons. Okay? So 1 newton, obviously they gave credit to the guy that came up with this, 1 newton is equal to 1 kilogram times acceleration due to gravity, or rate at which things accelerate towards Earth, which is 9.81 meters a second squared. So 1 squared. So 1 newton is equal to 9.81 kilograms times meters per second squared. Okay, remember that a newton is really equal to units of kilograms times meters per second squared. 1 is equal to 9.81. Okay. So I weigh about 160 pounds, and in the English system I could just say that's pounds mass, or actually I can say that's pounds force, but in the English system we don't actually differentiate between with 2 different units between mass and weight. There is a unit called a slug that's used for mass, but nobody uses it, or that is mass but nobody uses. So if I say my weight is 160 pounds force, I can convert that to mass in the metric system, which is about 72.6 kilograms. So my weight in the metric system would be 72.6 kilograms times 9.81 meters per second squared equals roughly 712 newtons. Okay? That's my weight in metric units. So, over here, we have the equation due to gravity. Okay. And that says that the force of gravity is equal to the gravitational constant times the mass of one object, in this case me, this is represented by a little m, times the mass of another object, which would be the Earth, divided by the distance between them squared, which in this case would be the radius of the Earth. Now you should actually add the distance to my center of mass from the Earth's surface, but it's so insignificant that it doesn't really matter. Okay? And the gravitational constant, which I should have written down here, is equal to 6.67408 times 10 to the negative 11 meters cubed over kilograms times seconds squared. Okay? So if you plug the mass of Earth, which I have written here, which is 5.9726 times 10 to the 24th kilograms, really big number, my mass, 72.6 kilograms, and the gravitational constant, and the radius of Earth, which is 6,371,000 meters, you will get 712 newtons, roughly. Pretty close. Close enough to say it's the same. To say that to accept the fact that, well, the assumed fact that gravity is causing this weight. And that's why I have weight is equal to the force of gravity on here. Okay? This is what is taught in physics. That this force of gravity actually creates my weight, but there's just two different ways we can calculate it. Okay? But Newton came up with this before he came up with the equation for gravity. And in fact, Newton only proposed the equation. He didn't actually finish it. He said, from looking at the solar system model and watching things in the sky that he thought, or he assumed were orbiting Earth based on Copernicus' work, that the force of gravity was proportional to the mass of one object times the mass of another object divided by the distance between them squared. Okay? He said they're proportional, they're not equal. So what this means is, if either one of these masses go up, or both of them go up, the force of gravity also goes up. But as the distance between them increases, the force of gravity goes down. And as you can see, this is square, so distance plays a big part here. So, he eventually proposed that he needed this big G up here, this gravitational constant. And he didn't know how to determine that, but he did know that the units would be what we have right here, meters cubed over kilograms times second. Now, he might not have been using the metric system now, I haven't actually looked into that, but he would have been using something similar, so I'm just going to assume that he used metric units. Because if you combine the units in this proportion right here, you would get, assuming the masses are measured in kilograms, you would get kilograms squared over meters squared. And if you multiply that times this factor down here, you will end up with kilograms times meters a second squared, which is equal to a newton, or a unit of force. Okay, just like I showed in the original equation, the original bread and butter equation over here. So, that said, he theorized that there was this gravitational constant, but he didn't actually figure it out before he died. And it wasn't until a little over 100 years later, about 120, 130 years later, that a man named Henry Cavendish came along. Henry Cavendish was very wealthy, and he did a lot of things apparently. I've listened to some very respected physics teachers praise his work, and studied some of his work, but mostly what I was interested in was how he determined this gravitational constant. Okay. Cavendish apparently had a lot of property, a lot of money, and he set up an experiment where, get rid of all this. Now let's go back to where we just have these two equations. You know, they haven't figured out the big G yet. They do know the radius of Earth, though, because they knew the circumference. So they knew the radius of Earth, but they didn't know big G, and they didn't know the mass of Earth. Okay? So going back to Cavendish in 1798, Cavendish built this box, this wooden box on his property. Looks something like this. Okay? And in this box, there was a pulley with a rope leading outside the box, something like that, a little handle on it. And what hung from it was this thing called a torsion rod.
something like this. And on the ends of the rod were these large lead balls. And on the inside were these smaller lead balls. Something like this. Pulley right here. And he used lead because it's very massive, it's very dense. And he, apparently, according to the history, he knew that he had to get away from the box because his gravity, his mass, would affect the experiment. Assuming that this is correct, that the force of gravity is, there's a force of gravity between any two masses, not just the Earth and us. All masses have a force of gravity on each other, or create a force of gravity on all other masses based on this equation and the proportion that Newton came up with. So he somehow set up some telescopes that went back to his house. Keep his house off the board, just assume his house is down here somewhere. So he could observe this experiment, and somehow he calculated big G from this. Okay. Well, when I started researching this, I said, okay, well, let's see some examples of a modern day torsion rod experiment that somebody's built that shows how this works. Well, I couldn't really find one. I actually had a lot of trouble finding one. Actually, one of the physics professors that was praising him had a little model that he held up and was joking that his TA couldn't get it to work and got frustrated with it and gave up. And I'm thinking to myself, over 200 years later, we don't have models of this, or repeats of this experiment all over the place that determine big G? It didn't make much sense to me. So I said, okay, well, going back through the history, let's assume that he did this somehow. He's a really smart guy, and we just haven't been able to get it to work again. Okay? So, Cavendish determined big G through that torsion rod experiment. Okay? So he calculated it to be the value that we're still using, which is 6.67. 408 times 10 to the negative 11 meters cubed over kilograms times seconds squared. Okay? He determined that from that experiment. Let's assume that's correct. So now he must have been really excited because he knows what this big G is. He knows what his mass is, or any other mass of an object on Earth. He knows what the radius of Earth is. So he can set these two equations equal to each other. He knows that weight and the force of gravity are equal. So what he did was, you can look this up, this is exactly how this was done. Weight, which is equal to mass times G, or the mass of the man or whatever object he's using, in my case I'm going to say me, is equal to big G times the mass of the man times the mass of Earth divided by the radius of Earth squared. Now immediately you can cancel the mass of the object, or me, out, because they're in the numerator on both sides. This is really mg over 1. Okay? And now, let's come up here. You can solve for the mass of Earth. You can multiply the radius squared times both sides, and that comes over here. Cancels on this side. And then you can divide by big G. So you get me, and this is basic algebra here, is equal to little g, the acceleration due to gravity, or the rate at which things accelerate towards Earth, times the radius of Earth squared divided by big G. And that is how the mass of Earth is calculated. That is the mass that NASA has on their fact sheet, where I got all this information about the Earth's radius and the mass of Earth and everything for this problem. Okay? So I looked at this and I said, okay, that makes sense, but I still had the question in my mind saying, wait a second though,
why can't we do this torsion rod experiment now? You know, there's some. I looked into this more, and right now there's debate going on about what this big G actually is. Some people are arguing and saying it's different, and they're doing experiments on an atomic and a subatomic level where they're looking at particles with very powerful microscopes and observing how they're attracted to each other, which they say is because of gravity. Now, I can't go buy an electron microscope and do those experiments myself to check it because I don't have that much money. And I don't want to try to build a torsion rod experiment because from everything I read, it sounds like it's not going to work. So I'm also going to spend a lot of money on that. So I'm really questioning, this big G. How did they come up with that? But then I started to look at this algebraic expression that was written. Get rid of big G again. Say, well, what if they were so sure about this equation due to gravity, or this equation of gravity, that they were having trouble coming up with G, that they did something else to determine it. What if they did this? Or Cavendish did this? What if he said G is equal to the acceleration due to gravity, as he would have called it, times the radius of Earth squared times the mass, or divided by the mass of Earth. Of course, he doesn't have the mass of Earth, right? Well, he does have the radius of Earth. And at that time, they definitely knew how to calculate the volume of a sphere. The volume of a sphere is equal to 4/3 times pi times the radius squared, or cubed actually. In this case, it's the radius of Earth. And so since they know the total volume of the Earth, they know that if they could figure out the average density of Earth, they could multiply that by this volume and get mass. If at the time they would have known the density of water and the density of sand, the density of ground rock, the density of iron, the density of gold, the density of silver, the density of all these things were already determined. And to determine the density of something, it's really just the mass per unit volume. For example, we'll call them rho. Call rho density. Rho water is equal to 1,000 kilograms per meter cubed. What that says is in 1 cubic meter, if you have you have something that holds a cubic meter of water, it weighs 1,000 kilograms. If you have something that holds 2 cubic meters of water, you say the density of water 1,000 kilograms times 2 cubic meters. You see the cubic meters would cancel. You get 2,000 kilograms is how much it would weigh. Okay. So you definitely know the density of water back then. You definitely know the density of, let's say sand and soils, which is roughly 1,200 to 1,600 kilograms per meter cubed. And they definitely knew the density of iron, because they were building things out of iron a long time before that. We'll call that rho I. And that is equal to 7,780 kilograms per meter cubed. Now, whether they were using metric units again, I don't know, but they would have had their units that could be converted to the units I'm using now, or the metric units I'm using now. Now, based on the volume of Earth, let's call that VE, the volume of Earth is actually 1.083 times 10 to the 21 meters cubed, okay? If you use NASA's fact sheet with their mass of Earth, which is 5.9726 times 10 to the 24th kilograms, and you divide that by the volume of Earth, you will get an average density of Earth, I'm going to call that rho E over here, of 5,515 kilograms per meter cubed. Okay? So, looking at this, just looking at water and soil, water is, well, the average density of Earth is over 5 times greater than the density of water. And water is actually pretty dense. If you've ever done a belly flop into a pool, you've seen you've experienced how dense it is. But, the average density of Earth is 5 times that of water. It's also a lot greater than soil and sand, which is really ground rock. But then you look at the density of iron and notice that actually the density of Earth is pretty close to the density of iron, based on everything that was calculated, the mass that came from this relationship up here. So I started thinking, this is pretty high, and that's exactly why we theorize that the Earth has an iron core, because this is the average density of all the stuff in Earth, all of the elements, everything on the periodic table that we know. Now, at the time, they didn't know all the elements on the periodic table, but they knew a lot of things. So what I'm saying here is, if you follow where I'm going with this, how do we know they didn't guess, or that Cavendish didn't guess this mass of Earth, and then just use it to solve for G, and then do the opposite and say that he did this, that he solved for the mass of Earth using that value of G? It's the same thing, just based on the algebra. And then if you plug both of those values into this equation up here and use the mass of any object, whether it's a man, a horse, a carriage, anything, and use the radius of Earth, you're going to get a force that's equal to the weight you get for that same object if you just multiply the mass of that object's time the acceleration due to gravity, or the rate at which the acceleration at which things fall towards Earth. Seem far-fetched? I don't know. The fact that we can't really get this experiment to work, this torsion rod experiment to work, is perplexing. Very perplexing. We have to trust that they didn't do this. But what if they did? Our entire solar system model stems from this. Assuming that this is correct. Assuming that this big G, this gravitational constant, is correct. So, I don't know. I don't know what to think. But one thing I do know, based on my research, another thing I found out based on my research, is that Cavendish and Newton were both Freemasons. It's a very big club. And back then, the average person couldn't even write their own name. So people slowly were introduced to the sciences. More and more people were introduced to the sciences over the years, and it wasn't just the wealthy people over the years. And I know there's a symbol out there that a lot of people have been trying to figure out. It looks something like this. You ever seen one of these before? Found them on a Freemason lodge. It's kind of an ominous symbol. First time I saw it, I was like, what was that? What is that? It's very strange. Compass and a protractor. The big G in the center, but what does that stand for? I don't know. Could just be a coincidence. Some people think it means geometry. Some people think it means God. I don't know. Some people even think it means Gnosticism. I've done a little research on this. Who knows? But maybe that's just a coincidence. I'm just asking questions. But in the next episode, we'll look at the relationship between this equation and the centripetal force equation, and how it was used to develop our solar system. Until next time, peace. Hi, I'm Brian Mullins, and this is Balls Out Physics, Episode 3, Centripetal Force, Gravity, and the Sun. Now before you watch this episode, if you haven't watched Episode 2, please go back and watch that, because this episode is really a continuation of that episode, where we talked about the bread and butter physics equation, F equals ma, and the equation for gravity, over here, Fg equals the gravitational constant, which the episode was titled, times one mass times another mass divided by the distance between them squared. Now, in that episode, I focused on the fact that the gravitational constant may have been calculated by estimating Earth instead of through experimentation, as we've been told. There's really not a whole lot of evidence showing that these experiments have worked. We're told that they worked. We're showed, there's articles out there showing pictures of modern day torsion balance experiments that say that they work, but a lot of people out there say they don't work. And I've never seen any replica of the original torsion balance experiment that Cavendish did, or Henry Cavendish did in 1798, which I'd really like to see, because that's really where it all started. But anyway, even if they did determine this constant through experimentation, it doesn't really matter, because of what I'm about to cover, in my opinion at least. So, diving in, this episode's really about the relationship between centripetal force and gravity, or setting them equal to each other, because the gravitational force that's supposed to hold our Earth to the sun, make it orbit the sun, is really a centripetal force, and this is the theory. Okay, so what a centripetal force really is a force directed towards the center of a circle. So a ball on a string is the best way to give an example of this. You have a ball or a mass, a little foam spherical Earth here, and a string representing the force pulling it towards the center, which in this case would be my hand, where you could say that was the sun. So you spin this around. Okay, the tension in the string is the force. Okay, and that creates a velocity. The ball resists that force by traveling in a circle around the center point, or the sun, in the case of the solar system model. Okay. So I have written down the equation for centripetal force over here. It says centripetal force is equal to the mass, or the ball, times the velocity squared divided by the radius. So the velocity would be the speed that it's traveling at around the circle. The radius would be the length of the string in this case. Or if you look at the solar system model, which I've got drawn right here, with just the Earth and the Sun, it would be the velocity, the instantaneous velocity of the Earth at any point around the circle, and the radius would be the distance from the Sun, and the mass, of course, would be the mass of Earth. Alright, so it is the mass of Earth, not the mass of the Sun. Remember that. So, this equation is really derived from F equals ma. Like I said, this is the bread and butter equation of physics. The only difference here is we're dealing with angular acceleration, or centripetal acceleration, whereas in the last episode we were talking about the acceleration towards Earth, or acceleration due to gravity, as it's called. Okay. So, just to show how this works, acceleration, angular acceleration, or centripetal acceleration, call it AR, it's commonly called, is equal to v squared over r. And let's say, just for a quick example, that when I'm spinning this, it's traveling at 1 meter per second, and let's say that the length of this string is 1/10 of a meter, just to keep it easy, which is 0.01 or 0.1 meters. So 1 meter per second over 0.1 meters. This is 1 meter per second squared, actually, up top, velocity squared, gives us 10 meters per second squared, which is pretty close to the acceleration due to gravity, or the acceleration at which things fall towards Earth, which is 9.81 meters per second squared. So the units are actually the same. Okay. However, in this case, the acceleration is considered to be acting towards the center of the circle, or towards where the tension in the string is for the spinning ball. Yeah. And if you remember in episode 2, I said that acceleration is any change of velocity. So since velocity has both a rate, as in miles per hour, kilometers per hour, meters per second, and a direction, if the rate remains constant but the direction changes, it is said to be constantly accelerating. So, theory is, since this Earth would be traveling around the circle, or it's actually, where NASA tells us it's elliptical, but they also use this equation, which is based on a circle, this velocity is constantly changing as it travels around the sun. Okay, the velocity, the direction of the velocity over here would be pointing down to the right. Okay, it's pretty simple. So, Cavendish came up with this value of big G, and then they calculated the mass of Earth, as you saw in the last episode. And then they could move on to the sun. They were basically assigning numbers to the solar system model that Copernicus had come up with a few hundred years before. Okay, so as I've written here, I have centripetal force between the Earth and the Sun, or the force pulling the Earth towards the Sun, is equal to the force of gravity. So what you can do is say these equations are equal. You can actually set Fc equal to Fg. So let's just say Fc up here equals Fg. Okay, but this is really m squared, or m, excuse me, times v squared, getting a little ahead of myself there, over r is equal to big G, the gravitational constant, times the little m, which is the mass of Earth, times big M, which we're going to say is the mass of the Sun in this case, over r squared. Okay? Now, at the time, they were pretty sure they knew how far away the Earth was from the Sun. They used sextants and other devices to get a measurement. Now, of course, the way a sextant works, as I've looked into, the Sun can either be a few thousand miles away and 32, 33 miles in diameter, or it can be 93 million miles away and have a diameter that's 100 times the Earth. It's either or, based on how a sextant works. I haven't used one yet. I'd really like to. Nobody uses them anymore. It's an old-fashioned tool, but it'd be really interesting. But anyway, let's assume that they were right, and the actual distance in meters is, or in kilometers, is 149.6 times 10 to the 6 kilometers, according to NASA's fact sheet. And so the mass of Earth, just like the mass of the man in episode 2, cancels out. Kind of funny how this gravity equation kills the smaller mass. Anyway, it's nature, right? That's what we're told. So now you have the mass of the Sun, you've got the velocity of the Earth, which you know because you know the radius of Earth, and you can calculate the circumference of the circle, or the distance it travels around the Sun, which circumference, I'll write that over here, is equal to 2 pi r. Okay? So they already knew the distance, so they can figure out the velocity, because velocity is really distance over time. So what they can do is say that velocity is equal to 2 pi r, and we'll call over big T. In physics, big T is usually considered a period, or the time it takes to make one revolution, which in this case they thought was 1 year, because the Sun does its thing in 1 year. 4 seasons it takes, though they tell us 365 and a quarter days, which actually comes out to 31,557,600 seconds, which is what you would have to do to make all these units work. But I'm not going to go through all the numbers. I'm just going to show the algebra to show how this was done. You can look this up. This is all over the internet. So we need to isolate the mass of the Sun. We have everything else. We have the velocity, which can be calculated with this equation. We have the radius. Radius is the same over here, and they have the gravitational constant, which who knows how that was really determined, but it doesn't matter. Okay, so showing some simple algebra here, you could say multiply this side times r squared over g, multiply this side times the same thing, r squared over g, just to show the steps. So r squared cancels, g cancels. Over here you've got r squared times v squared over g times r, and then this r cancels. So you really just have r times v squared over g is equal to the mass of the Sun. And that comes out to 1,988,500 times 10 to the 24th kilograms. Now this is many, many times more massive than the Earth. The Earth is actually 5.97 times 10 to the 24th kilograms, I think. Is that written down? Yep, roughly. So, many, many times more massive than the Earth is what we're told. Which, you know, see the solar system model, the sun appears huge compared to all the planets. So, with this relationship now, they calculated the mass of the sun. But as you saw in the example, the mass of the Earth that's orbiting the sun cancels. So, well, the first time I did this, I kind of got a little excited at first, but then I realized, well, the mass of whatever's orbiting the sun just cancels out. It doesn't matter. And so I said, well, what can we do now? You know, because I thought for a minute I'd get to go calculate the mass of Jupiter and Mars. For some reason, I've always liked Jupiter, and that was my first thought. And I said, well, no, you can't because the mass cancels out, as I showed. So let's go back. Get that equation back up here. What you can do, what people have realized though, is since v is actually equal to 2 pi r over the period, you can say v squared is equal to 4 pi squared times r squared over t, over the period squared. See, it's just this times itself squared. Okay, so going back to that original equation, we can write the centripetal force equation now with that original relationship. That is, we can substitute this for v squared, and that'll give you that'll give you 4 pi squared times r squared over r, because r was still on the bottom, and this t squared comes down here, over r times the period squared. This r cancels and that r cancels, so you get 4 pi squared r over the period squared, or big T squared. Okay? And then set that equal to big G times little m times big M, mass of the sun, divided by r squared. Okay? Now, mass cancels again. But what you can do now, since you know the mass of the sun, or what they say you can do now, is determine the distance of anything orbiting the sun if you know the amount of time it takes, or the orbital period of that object, right? This is what's currently done. So what this breaks down to is you need to get r by itself, because r is the distance, right? Once you get r, you can determine the velocity as well, according to the theory. So to get r by itself, we multiply this side times r squared. Let's do r squared over 1. And this side times r squared over 1. And that gives us 4 pi squared r cubed equals, cancels on this side, g times big M. And then we want to get r by itself over here, so we just divide by r pi, or by 4 pi squared. I'm not going to actually show the steps, but we'll just say r cubed equals g m, nope, I missed t cubed. And let me just write this out. What this actually works out to, instead of doing all the algebra for you guys, I can do it, I've already done it. And if you look this up, this is the period equation. R ends up being, so I'm not boring you with all the algebraic steps, the cube root of the gravitational constant times the mass of the sun times the period squared over 4 pi squared. Okay? That's what this breaks down to. You can solve for r. And so what they say is that if you know the period, for instance, Jupiter takes 11.86 years to do its thing. You know, we see it, if you pick a point in the sky and you record where it is in the sky, it will take 11.86 years to get back to that point. People have been watching these things, the wandering stars, as the ancients used to call them, or the planets, 8 of them. that, well, 7 we can see, we're supposed to be on one of them, since the beginning of time, as far as we know. So this is well documented. The period or the time it takes for each one of these 7 entities to do its thing is well documented. Okay, and so you would need to convert the time for Jupiter into seconds, and that is actually, just to throw a number out there, 374,198,400 seconds. It's a pretty long time. Lots of seconds. So you plug that in, you've got how far Jupiter is from Earth, right? Well, I don't really agree with this. And the reason I don't is because we got to back up here. The only thing that matters, according to this equation, is the mass of the Sun. The mass of Jupiter doesn't matter, so Jupiter could be a golf ball, or it could be, what they tell us, something with the mass of 318 Earths, roughly. So, based on this, the mass doesn't matter. What about this over here? This original proportion that I talked about in episode 2. As the mass of each object increases, the force of gravity increases. As the mass of one of those objects decreases, the force of gravity decreases. But the way I look at this, it's saying that the Sun controls only. Let's back up a little bit. Maybe I'm getting a little ahead of myself here. Go back to this original relationship. We don't need to do this anymore. We'll go back to just keeping it simple. You say the centripetal force Fc. You say the centripetal force Fc is equal to the mass of the object orbiting the Sun, which we still have as the Earth here, or Jupiter, or Mars, or whatever you want it to be, times the velocity of that planet, or wandering star, divided by the distance from the Sun, r, is equal to the gravitational constant times the little m, which is the mass of Jupiter, or Mars, or Earth, or whatever, times big M, which is the mass of the Sun. I'll write Sun here to clarify that, times the distance that object is from the Sun squared, and that's equal to the force of gravity. These are said to be equal, and this is how the solar system was built, or that's how we applied numbers, or they applied numbers to our solar system. Okay. Well, this math is canceled. So now, if you just cover this side and look over here, this is no longer a force. You need this mass to have a force, right? Just like you need a force down here. Or if you cover this side, this is no longer a force because the gravitational constant needs the units of mass, in this case kilograms squared. So this is no longer a force. So if you cancel out these little masses, you cancel out the force. You can't have your cake and eat it too, so to say. This defies logic, in my opinion. How can you say that the mass of the object orbiting the Sun does not matter? It does, because that's what creates the force. This says that the force goes away, so then what happens? This doesn't make sense. But if you go back to that equation that I showed, you say R equals the cube root of G, which you can solve from this, just to show this again, times the mass of the Sun, times the period of the object orbiting the Sun, how long it takes to go around one time, divided by 4 pi squared. If you take the period of any of the planets, I did all the planets, even Earth, or the wandering stars, and you plug this time in, you get the exact radius, roughly the exact radius that NASA has on their fact sheet from every one of the planets, their fact sheet. So, you know, I've looked into this for a while and I've been aware of how masses are calculated. So you say, how do you figure out the mass of the object that's orbiting the Sun then? Because this says that the Sun wins. The mass doesn't matter. I don't know. Well, what they say is they observe the object. They observe Jupiter, for example, and they observe the moons that they tell us are orbiting Jupiter. and they can tell by the tug and the pull back and forth, say like, I don't know, let's say that this is Jupiter and this is a moon, and they can see the little wobble it gets from the moon going around it, the wobble effect on the planet, that they can estimate the mass. Okay, and maybe they compare it to what they think is the relationship between the sun and the earth. But it's all from observation. It's kind of guessing, I think. Lots of guessing. When I took astronomy, I was kind of blown away by this, especially because NASA tells us that these are facts. But it doesn't matter if their estimation's wrong according to this equation, because mass doesn't matter, right? But it does matter. This equation right here, this gravity equation, causes these two forces to cancel out. Just like in episode 2, when you set this equation equal to the weight equation, the smaller mass is eliminated. This is... how have we gotten this far? Is what I'm asking. I mean, this is my opinion, but I don't understand how the smaller mass cannot matter. And both equations depend on that smaller mass. Just because the mathematics works doesn't mean it's logical. This is a huge mistake that I think we've been making for years. If somebody writes an equation and the math works, things cancel out, and you get a number, and we think we've actually figured something out, but you always have to employ logic. Actually, Tesla had a lot to say about this, and if you know anything about Tesla, I think he's the greatest engineer that ever lived, but that's why we have alternating current. And it's kind of strange that we don't really hear much about him in our history books. Anyway, so I started thinking about this, and well, I started really thinking about this equation and how it came about, and how it makes this guy over here win. Sun wins, sun controls. And I started thinking about who came up with the solar system model. And that was a man named Copernicus. You can look this up. Copernicus was the first person to propose the solar system model. And well, Copernicus was a pagan. Pagans worship the sun. Interesting. Copernicus proposed the solar system model to the Church of England in the early 1500s, maybe 1513, 1514, somewhere around there. I might be wrong on that, but early 1500s. He proposes this model to the Church of England. You can look all of this up. And the Church of England says, yeah, that sounds great. We're just going to get rid of 1500 years of Christian belief and or Catholic belief, I guess if you want to call it that, and we're just going to adopt this model. Because the Bible actually says the earth is flat and it doesn't rotate. And it says that everything goes around us. Now some Christians have argued that, but my Bible, I was raised Catholic. I don't really consider myself anything. I consider myself my own religion, the 1 in 7 billion religion. That's a separate issue. But you turn to page 5 in Genesis, and we've got this. New American Bible, Catholic Bible. What's that? That shows a flat earth with a firmament and the stars and the sun and the moon going around us. That's strange. And they would just give it up because a pagan came and told them that everything goes around the sun? You know, people hammer science and say that science is the answer. They don't realize that the science of their world and this solar system that we're supposed to live in actually came about through religion. Very strange to me. I'm really starting to doubt things. What's actually funny is in November of last year, I was joking with my roommate about the Bible and saying, I don't really believe this, because I opened this page and said, look at this flat earth thing. I mean, this is ridiculous. I was drinking beers with him and we were laughing about it. I mean, talk about putting your foot in your mouth. So, something to really think about. You know, the Freemasons came along, obviously, or not obviously, but I said in the last episode that Newton was a Freemason and so was Henry Cavendish. And if you study Freemasonry at all, you'll find that they have a lot of sun symbolism. They really seem to like the sun. Is that a coincidence? I don't know. You know, I'm asking questions here. Like I said, if I'm proven wrong, great. You know, I can go back to living a normal life, I guess, what we thought was a normal life. But think about this relationship and how this equation, in my opinion, seems to be designed to do exactly what they wanted, a solar system, to make us revolve around the sun, or to make us worship the sun. Are we worshiping the sun through science and we don't even realize it? You should look into some of these organizations, some of these secret societies that seem to be prevalent throughout politics, science, or even religion. The Vatican has a lot of sun symbols too, which I find very strange. Why did they give up what the Bible said in 1500? Something else to really think about. You know, since I started studying this, I've started watching the sun. Now, I don't recommend looking directly at the sun because you'll see spots for a little while. But if you notice, the sun comes up in the east, comes up above the horizon in the east, and as it moves through the sky in the day, it starts off, the diameter appears to be a little bigger than it does at midday. And it's very noticeable when you look at the moon this way. The moon does the same thing. The sun and the moon move through our sky at the same way, really. I mean, of course, the sun is moving faster than the moon. It seems like, you know, the moon has a different period compared to the sun, but they both do the same thing. You would think if one's going around us and we're going around the other, and the other moves through our sky because we're spinning around our axis, you know, if we live on a ball Earth, you know, if this is our axis and we're spinning and this is what makes the sun move through our sky, that they wouldn't do the exact same thing. Actually, I think it would be very clear to us that we are rotating relative to the sun and that we are moving around it. But they both do the same thing. Think about that. How is that possible? I think they're both going around us. How can they not be? I don't know. Maybe I can be proven wrong on that. But if you want to look at the sun, I highly recommend getting a welding mask. It's really cool to look at the sun through one of these because it looks green and you can actually see that it's about the same diameter as the moon. It looks identical to the moon when you look through it through one of these. So, asking questions again, but pay attention to the sun and watch the moon and ask yourself, what do you think? Are we going around the sun or is it going around us, just like the moon? I don't know. But I'm going to keep watching it because it's interesting. And I really want to know what my world is. We all need to work together and figure this out. So until next time, we'll be talking about a thermosphere and maybe something else in episode 4. See you then. Peace. Hi, I'm Brian Mullins, and this is Balls Out Physics, episode 4, the ISS, satellites, and the thermosphere. When I first started researching flat Earth theory, one of the first things I had to accept, if I was going to even think about the possibility, would be that NASA and all of the photographs or composites, as they are actually called, or in video, whatever you want to call it, from space is fake. And I mean, that's a giant leap you have to take to to accept something like this, or to even consider it. And so I started watching videos that people had produced showing that the ISS was a hoax, and you know, that satellites were fake. A lot of people, there were videos showing that on spacewalks, when it looked like they were on space, people caught a bubble rising from an astronaut's helmet, or a guy with a scuba tank inside the ISS in a window, and just other things like that. And so I first started seeing that stuff, and it was pretty convincing, but at the same time, I thought, well, it's not definitive proof, because how do I know that this stuff hasn't been edited in to sway opinions, because there are people out there that believe the earth is flat and they want everybody else to believe it too. So I remained skeptical, but I also was doing my own little experiments on Earth with binoculars and just seeing how far I could see over the horizon, and drawing distances in AutoCAD and doing calculations and finding that I was able to see things much farther away, and observing the sun and the moon and the stars and things like that. And so my opinion started to sway a little bit, but I still was trying to prove it wrong. But I'll never forget the moment that everything clicked. And that was on a Friday night. I was just watching videos, doing my typical thing, just wondering, trying to prove these things wrong that I was seeing. And I don't remember what video it was, but the narrator in the video said, how are there satellites and a space station in the thermosphere layer of the atmosphere when the temperature gets up to 2,000 degrees Celsius? And that's when everything clicked. I remembered, oh wow, I remembered from astronomy, my professor talking about the temperature in the thermosphere. And I remember her taking a marker like this and holding it out, and held it in front of the class like this, and she said, the temperature in the thermosphere layer of the atmosphere is upwards of 2,000 degrees Celsius, or can get up to upwards of 2,000 degrees Celsius. But you can't actually measure the temperature because the gas particles in the thermosphere are spread so far apart that there are not enough of the particles collide with the tip of the thermometer to make it show a hot temperature, because heat is actually kinetic energy. And a thermometer works by measuring basically the collisions, the energy being transferred to it, and that's why it shows you what the actual temperature of the liquid or the air or whatever is. And so I remember sitting in class and thinking to myself, well, how did they measure the temperature in the first place? How do we know it's 2,000 degrees Celsius if you can't measure it? And I thought about maybe thermal imaging or something, but still you have to be measuring that kinetic energy. So it didn't make sense to me. But at the time, I didn't put two and two together and realize that that's where the majority of LEO, which are low Earth orbit satellites, and the International Space Station and the Space Shuttle used to be. What they used to, or the Space Shuttle used to be, but everything else orbits the Earth. And so when that hit me, I said, wait a second, this can't be. And I thought about the thermometer. I really started to think about thermodynamics. And I had to take thermodynamics to get my engineering degree, and so I went and I pulled out my thermodynamics book. I actually kept all my books. I didn't know I'd be using them for something like this later in life, but I knew I wanted to have them for reference. And so I got my thermodynamics book out, and I went to the first law because I remembered what the second law was, but I wanted to read them both again. So when you go and you read the first law of thermodynamics per this book, says, the first law of thermodynamics is simply an expression of the conservation of energy principle, and it asserts that energy is a thermodynamic property. And that's basically a more complicated way of saying what I just said, that heat is energy, kinetic energy. Okay? And the second law of thermodynamics asserts that energy has quality as well as quantity, and actual processes occur in the direction of decreasing quality of energy. And what that means in terms of heat is that heat, something that's hot will move to a colder area, because the energy in something that's hot is higher than the energy in something that is cold. So they give an example, and they say, for example, a cup of hot coffee left on a table eventually cools, but a cup of cool coffee in the same room never gets hot by itself. The high temperature of energy of the coffee is degraded. It's transformed into a less useful form at a lower temperature once it's transferred to the surrounding air. So they give a little picture, they show a little picture of this. I mean, you can probably imagine a cup of coffee cooling down, but they show that if the cup of coffee is 70 degrees Celsius and the surrounding environment is 20 degrees Celsius, eventually the heat will dissipate from the coffee and become the same temperature as the room around it, or the area around it. I mean, this is common sense. Everyone knows this. that if you leave something out that's hot, soup or whatever, and you don't consume it in time, it's eventually just going to be room temperature, and it may not be as enjoyable. So, keeping that in mind, hot goes to cold. Now, before I took thermodynamics, I actually knew this pretty well because my dad is a mechanical engineer, and he basically groomed me to be an engineer from birth because that's what he is and that's what he knows. And he told me hot goes to cold. He wanted me to know that. It was something he was adamant about. But the way I really learned it is whenever I would leave the back door open in the summertime, he would say, "Brian, shut the back door. You're letting the heat in." But in the wintertime, it was, "Brian, shut the back door. You're letting the heat out." He always said it right. He always said that the hot goes to the cold. And so that was always ingrained in my head. And then when I took thermodynamics, I actually found the class very interesting because it built off of that basic principle that hot goes to cold. So why this all clicked for me, and you may or may not agree with this, is that I don't understand how this heat is not being transferred to the International Space Station and all the satellites up there. But first, let's look at how the atmosphere is constructed, or the layers of our air exist above us. If you go to Google Images or Google Images, or just get on Google and type in layers of the atmosphere or temperature, you might find this chart. I found this one. I decided to print this one out because it was the most clear. They vary with elevations and where the delineation lines are, but I'm just going to use this one to explain this. Okay, so basically there's 5 layers of the atmosphere or of our air. And we are in the troposphere. You might remember this from general science in middle school or whenever you took something like that. And when you go up in elevation in the troposphere, the temperature decreases. If you go up in the mountains, it starts to get cool. You might have experienced this. I mean, it's very common knowledge that as you go up into the mountains, the temperature gets cooler. And that always seems kind of strange, right? Because you're getting closer to the sun. But there's reasons for it. I'm not going to get into that in this video. But the temperature gets colder and colder, down to around negative 50 degrees Celsius at about 10 kilometers over here. And then you get into the stratosphere, and temperature actually starts to increase a little bit, which I always found kind of strange that it goes back up, and up to about 50 kilometers. And then you get to the mesosphere, and then the temperature starts to decrease again as you get into the next layer, and it gets down to about minus 100 degrees Celsius, which is about 100 degrees less than the freezing point of water. And then when you cross into the thermosphere, though, the temperature starts to slightly increase from about 90 to 100 kilometers based on this chart, and then it rapidly increases. I mean, it shoots up over 20, 30 kilometers. I mean, from negative 50, negative 100 degrees up to about 500, 1500 per this chart. Some say 2000 degrees Celsius, some say 2500 degrees. There's all kinds of numbers out there, but everybody can agree that it's really, really hot. 2000 degrees Celsius is very hot. To take this into consideration, or to put it in perspective, I mean, the melting point of aluminum is 660 degrees Celsius. And satellites and the ISS are definitely going to have a lot of aluminum on them. They're also going to have a lot of plastic on them for circuitry, circuit boards, and things like that. And plastic melts at around the boiling temperature of water, which is about 100 degrees Celsius. So keep that in mind. So you see the temperature keeps going up into the exosphere, and it keeps going up and up and up off the chart. And the exosphere is basically the last layer of the atmosphere, where the gas thins out so much that eventually you get to a point where there's no more gas and you're in space. I mean, this is what I was taught in astronomy, and this is the general idea. I don't know if I said it exactly right, but that's the accepted theory. Okay? So those are the layers of the atmosphere. But I wanted to focus on the thermosphere because that's where the majority of LEO satellites are. The ISS is considered a satellite since it orbits the Earth, as is the Moon, and in mainstream astronomy. And so I drew here the thermosphere on the board, and I chose to say it starts at 100 kilometers because there's other charts out there that show 100, and it's just easier to use 100. And I also said that the top of it is at 600 kilometers because there are other charts that show it at 600. And NASA tells us that the Hubble, Fermi, and Spitzer, Hubble being the most famous telescopes, are around 560 kilometers, and they say that they're in the thermosphere. So that's why I chose 600. And these red dots on the board are supposed to represent the air, the gas particles, which basically the atmosphere up there. Okay, and red because they're hot, and you know, I've also got the ISS and satellites up there, and down here I've got the lowest LEO, which is supposed to be around 160. I mean, 160 kilometers, and there's supposed to be thousands of satellites out there, so there's not just one down there, there's multiple, but this is just a representation. You know, obviously not the scale. And so, when you start to think about how heat works, heat and pressure works, if you, or gas it works, think about a pot to visualize the air in the atmosphere. You think about a pot on the stove. You fill it with water, put it on the stove, you say you want to boil some water. Put it on the stove, and you turn the temperature on high, okay? And eventually, about 5-10 minutes, you've got boiling water, and sometimes, you know, the top will start to rattle around, depending on how much water and air you have in there, what the ratio is. The top will start to rattle around, and it can even blow off. And that's because pressure and temperature are proportional. This is one of the things I found most interesting in thermodynamics, and one of the things you learn. As you increase temperature of a gas or a liquid, it wants to expand. And if you have it contained in a vessel like this, the pressure will increase because the particles are all bouncing off of each other, and it's trying to move out away. So I tried to illustrate this, that at the lower temperatures of the thermosphere, the air is going to be more dense. If you see, I've got more dots down here than I do up here because the gas starts to try to expand away from each other because it's hot. The hotter it gets, the more the particles want to get away. Okay, but the particles are so far apart where all these satellites are that there's not enough of them colliding with the satellites and the ISS and everything to make them melt. That's basically what my astronomy professor said with the thermometer example, and this is the general accepted excuse or reason for why these satellites aren't melting and why astronauts aren't burning up, and that's it. Okay, and so it kind of makes sense. Someone pointed out on my channel, he made a pretty good comment. He said, well, what if it's like an oven? You know, when an oven's hot, you put your hand in the oven, and your hand doesn't burn up immediately. You can put your hands into the oven because the air is pretty spread out. You know, but if you keep your hands in there, eventually they will start to cook. Okay, and I thought that was a good example, and it made me really start thinking about this. And I thought, well, if something's hot, you know, to keep it hot with the surrounding cooler environment, you have to keep putting heat into it or energy into it to keep it hot. So going back to the pot example, the pot's on the stove, the lid's rattling around. You say, oh, the lid's going to blow off, so you turn the temperature. You just turn the dial off, turn the heat off right away, and usually the lid stops bouncing around pretty quick, and the pot and everything cools down pretty fast because the room temperature air around is so much lower. And that gets into potential difference. The lower the temperature, the more mass around something that's hot, the quicker the temperature can dissipate to the surrounding environment. Okay, so I started thinking about the thermosphere in this sense, and all these red particles, you know, or these gas particles, the red dots representing them. Something's got to keep them hot, right? Because space is supposed to be cold, very cold, because there's nothing out there. And the mesosphere below the thermosphere is also minus 100 degrees Celsius. If you can see down here, I drew a bunch of blue dots and tried to show them very dense because the temperature's cold, so they're closer together. Okay? And another thing I wanted to point out, this is kind of a side note, is that when you heat things, every material expands when you heat it. All materials expand. And you know, if you remember solid, liquid, gas from basic science courses, they talk about, you know, generally liquids become gases as you heat them, and so all materials expand as you heat them and contract when you cool them. But there is one material that does something different when it's cooled, and that's water. Water, when you heat it, it expands, just like in the example with the boiling pot, becomes steam, and the hotter the steam gets, the more it wants to expand. I think there might be a plateau, though. I can't remember. I've got to get back into that. But it does expand. And when you cool it and it goes to its liquid form, it cools and cools and cools down to the boiling point of water is 100 degrees Celsius and the freezing point is 0 degrees Celsius. And water actually gets its most dense in its liquid form at about 3 or 4 degrees Celsius. There's been experiments and research on this. I'm not sure what the exact temperature is, but somewhere around 3 or 4 degrees Celsius, water is actually its most dense in its liquid form. And then when it freezes, something amazing happens, I think. It suddenly expands. All the particles fly away from each other and they freeze. I mean, they don't stop moving. They're still moving. I mean, solids still have particles moving in them, or atoms, molecules, whatever you want to call it. But the water freezes and becomes less dense, and that's why it floats, because it's less dense than the water. That's pretty amazing when you think about it. I mean, water makes up our bodies, and 75% of the Earth. 75% of our bodies, 90%, and some people say. I mean, it varies, and it's the life giver, in my opinion, of all materials. I mean, we have to have water, and it does this amazing thing that nothing else does. I'm getting a little off track there, but I think that's a very interesting side note and something to keep in mind when you're thinking about things heating and cooling. Okay, but back to the thermosphere. Okay, there's gas here, and there's air in the thermosphere, represented by these particles. And they're hot, really hot. You know, as you get up to the top, you know, they get around 1,500, 2,500 degrees Celsius, as I've written up here, and they get in the exosphere. The air particles are still hot, but they're very far, they're spread apart, and not enough of them are colliding with the objects that are up there. So that's why we're told that they don't burn up. Well, something's got to be keeping the thermosphere hot. And what is that? Well, obviously it's the sun, because that's what's supposed to warm the Earth. But that's also kind of questionable, because, you know, the reason that heat isn't transferred to the satellites is because the air particles are too far apart. Well, in space, there's supposed to be no air, no gas particles. You know, okay, I had to cut, but there's no air in space, right? And so keeping this in mind, with the particles being too far apart to transfer heat to the satellites in the space station, how does heat from a sun that's 93 million miles away travel through the vacuum of space to get to Earth and warm the Earth? That was always a big question for me, and it doesn't make a lot of sense. But it is accepted that electromagnetic waves can pass through space or through a vacuum. Okay, and light in astronomy, it covers the whole. That term covers the whole electromagnetic spectrum. And to give you an idea, from my astronomy book, here's the electromagnetic spectrum up here at the top. And you can see it's made up of visible light, which is the rainbow in the center, and that's a very, very small portion of the spectrum. And then there's ultraviolet, infrared, X-rays, gamma rays, and it's radio waves, of course. And you know, radio waves need to be able to travel through space for NASA to communicate with the space station, right? Or with the space station and Apollo missions, whatever. That has to be true for that to be, for communication to be true. And so, get an idea, you know, of how this would warm the Earth. In my book, there's another image that shows. I'll turn it this way. How much of light or the electromagnetic spectrum gets to Earth? And as you can see, only visible, a little bit of ultraviolet, and radio waves can get to Earth through the atmosphere. So by that logic, you would assume that with the atmosphere absorbing the gamma, X-ray, ultraviolet light, that's what's heating the atmosphere. That's what the particles are absorbing and warming, and that's what we're told. That these particles absorb that light, and that's what makes them warm. Okay, that's how they stay warm. Now, as I said before, you have to keep heating the system for it to stay hot, or the heat's going to try to dissipate and go into the mesosphere or to space. Right? Well, how come the electromagnetic waves or light that's hitting these satellites isn't heating them up? You know, they're there too. Something else to consider is if you've ever seen the movie Apollo 13, To kind of get on a side note, but this is related. In the movie Apollo 13, they don't make it to the moon, and they have a malfunction, and the whole movie is about trying to get them back to Earth, and supposedly this is a true story. Well, in the movie, on the way back, they're running low on battery power, and to conserve energy, they turn off the heater, and then all of the astronauts get very cold. Well, if you think about that, if the spaceship or the Apollo 13 ship is between the moon and the Earth, it's being bombarded by light. It's not shielded by an atmosphere or anything. So wouldn't it be really, really hot? Well, I mean, I guess since these things don't get hot, same logic. But then also, how does it get cold? It's a two-way street. If there's no air out there for the heat to radiate into, to move through conduction or convection, how does heat leave the Apollo 13, right? How did it get cold? It's got to have something to move through. Only light can transfer energy through space, as we're told. On Earth, you have to have some kind of medium for it to travel through. This is common accepted truth. The heat has to move through something unless it's light. And so the same thing goes for the space station. How does heat that builds up inside the space station get out? Right? Inside the space station you have astronauts, which the temperature of a human being is 98.6 degrees Fahrenheit, which is warm. I'm familiar with that scale, living in the United States, and that's pretty warm. That's actually hot. If it was 98.6 degrees in this room, I would be sweating, and so would the astronauts. And then you have electrical current throwing through wiring. Anytime electrons flow through anything that generates heat. And all kinds of systems on the space station. How does the heat get out of the station if there's nothing to dissipate it through? Right? There's no collision. There's not enough collisions with these particles to transfer heat into the station. So how does that heat get out? It would be really warm, if not hot, inside the station. And then, when you think about it, that means that there's some kind of barrier here. Around the station that doesn't allow. Basically, invisible barrier is formed. There isn't a barrier there. An actual, a theoretical, imaginary barrier is there that doesn't allow heat in or out because it's a two-way street, like I said. So, how does this work? They have to have a set temperature before they even get into the thermosphere. There has to be a nice, room temperature in the United States is usually 72 degrees Fahrenheit. And they look like they're in an environment like that when they're on the space station and wearing collared shirts and pants. Most of them, they probably want something that's comfortable so they're not sweating, and they look fairly comfortable. So how do they set that temperature? Heat can't go in or out. So going back to the electromagnetic waves and it's hitting these satellites, but they don't get hot. But if these gas particles absorb light and energy and get warm, these satellites are made of metals and very dense matter, and they're cool. They're going to absorb that light too. How do they not absorb the light? How does it choose to only warm the atmosphere but not the satellites? And not the Apollo spacecraft, or not any of the probes that have been out in space that are getting hit by direct sunlight? It doesn't add up to me. It defies logic. And another thing to think about is these black lines here are supposed to represent the solar panels on the ISS. You can look up an image of it on Google if you want to see it. I didn't draw a perfect picture of it, but that's generally what it looks like. Solar panels absorb light to create electricity. And if the temperature gets up to 1500 to 2500 degrees Celsius up here, let's say it's 1500 as I've got over here. I'm just taking approximate temperatures based on that chart I showed at this elevation. I've got 1000 down here for the LEOs. Those solar panels absorb electricity, or absorb light to make electricity, and they can work in 1500 degrees Celsius temperatures. That's very, very hot. And okay, let's say they can, and they're getting hot, and they're connected to the station. Shouldn't they be transferring heat into the station? Through the matter that they're connected with. I've heard people say that the satellites and the ISS have like a reflective material on them that reflects the light. Okay, but that would work for the station. But what about the solar panels? They are absorbing the heat, and the heat. If you hold a steel rod and you light a fire under one end of it, eventually the heat will travel through to the colder end of the steel rod on the other side. Metals conduct heat. I mean, basically all matter does. So heat will distribute itself through all matter. Hot goes to cold. It'll go to the colder pieces of matter. So how does this work? And if there is really a reflective material that can then reflect the light back off of you, I want clothes made out of that for an August day in Florida. Because when the sun is on you in August and early September in Florida, it is miserable here. It is very, very hot and it's humid. Yes, the ambient temperature around me is also warming me. But when I go in the shade, it's cooler. So if you can get this reflective material, I really want some. I want a hat made out of it, everything. Of course, they'd probably say it's very expensive. So this, in my opinion, defies the second law of thermodynamics. And we write laws. Science says something's a law. I don't agree with this, but we basically say that nature has to follow that law all the time. I think that's a little arrogant for us to do, but that can be seen in the whole theory of dark matter. That dark matter is theorized because galaxies appear to spin so fast that there's not enough mass in them that defies the law of conservation of angular momentum. So we have to theorize that there's dark matter to obey our laws of science. But this is disobeying the second law of thermodynamics. So we're contradicting our methods of analysis here and acceptance. So I can't believe that these things are here. I can't believe that any spacecraft have gone to the moon because they would get hot based on how all of this is supposed to work. And so I'm sure scientists and engineers have thought about these things before, and I did before I even started to question it not being real. But when you see a picture of these things, animations, really, because there are no real pictures of satellites, you can look this up, they're all CGI, they're all animations for some reason. Where you see astronauts on a space station or out on a spacewalk, you think it's there. So all these questions about the physics go right out the window. I mean, at least they did for me. But then when I say, well, wait a second, what if they're faking it? Then all of this comes roaring back. And you put the two together, and it really starts to seem like we're being lied to here. And I have to admit, it broke my heart when I realized all this, when all this clicked for me. I don't want to believe that this isn't there. I used to be such a space nerd, and I went and saw The Martian actually after I filmed my last Balls Out Physics series, and I got really depressed after I watched it. To be honest, within the first hour of the movie, I was sad. I missed the idea of humanity getting off of Earth and exploring the stars, but logic, I'm not going to let my emotions overpower my logic, because then I'm just lying to myself, and that's just silly. And I really hope that most people out there aren't doing that, because logic, we need to use logic here. And so go check out these hoax videos. Go think about things like when they're out on a spacewalk, they are always looking at Earth. They never have any equipment on the other side of the space station looking out into the great void of space. Well, people say that's because you can't film the fourth wall, or because, I mean, that would be hard to fake, I think, too. And then there's other things like, the inside shots when they're showing the astronauts. People point out that they look like they're harnessed, and if you think about it, you could fit every inside shot of the ISS we've seen could fit inside a 767 or 777. So you could use a combination of harnesses and a zero-G plane, diving and climbing at the right angles to create the zero-G effect. Because you can buy tickets to go on a zero-G plane, and I mean it's expensive, but you can do it and experience weightlessness. And we have videos from the inside of those planes. And those are a good thing to watch and to compare to some of the footage we see from live interviews with astronauts. Apparently Scott Kelly allegedly just returned from space after almost a year up there. And one thing I notice about him when he does his live interviews, or when he was allegedly on the space station, is that he always liked to end his interview with a backflip or a front flip, to show off that he's in space. But he's bald, and when he did that, you notice his face and his head get red. Well, he's supposed to be in space. He's supposed to be weightless. So when he turns upside down, it seems like the blood is rushing to his head like it would on Earth. I don't think that should happen in space, because unless you consider maybe centrifugal forces are doing that, and going back into episode 3, if you watch that, where there's a force pulling towards the center of a circle in rotation, but that's supposed to be balanced in space, which I'll go back and make a sub video to episode 3 to explain that. But it doesn't add up. It really doesn't. So I don't know what to conclude. I cannot believe that they're in space. I think after all of this that all space agencies have been lying to us. It breaks my heart, like I said, but I mean it's pretty obvious to me that it's all been faked, and that means a lot of countries are in on this. And a lot of people say, well, that's too big of a conspiracy. It can't exist. Well, just because something seems too big, just saying it's too big does not disprove all of the evidence that points to the fact that it is actually happening. And something else to consider is that every single country that has a space program also has a privately owned central bank. And governments, the media, and our education systems, in my opinion, do a very good job of keeping that information from us, that central banks are privately owned by big banks. And so most people don't know that. That's a huge deal, in my opinion. It's really not that far-fetched to me. I mean, the amount of lies I've seen from governments and media in my lifetime, it just doesn't add up. So think about this one. Think about this being real or not. Ask yourself, do you really think they're up there? Go watch ISS footage. Go look at pictures of satellites. Ask yourself why, when they're out on spacewalks, they never see the thousands of satellites that are supposed to be up there. You never see one go whizzing by. Or why they never, when they're inside the station, they don't show off more and show us the void of space from inside the station with a camera looking out. There's just not enough. I don't see enough to believe it's true. And then the physics is defied. So whether the Earth is flat or a sphere or concave, I don't know that really at the moment. I'm still working on that. I don't know if we have a working model of our world at all. But I know for sure that space, that men in space, human beings in space, is a lie. I don't think they've ever been there. And you may disagree with me, and that's fine, but make sure you prove it to yourself that they are there or they aren't there. Okay? Like I said, I don't want to believe it, but I have to follow logic. So, until next time, let's keep pushing for truth on this. And, well, one more thing I want to say is, last year NASA's budget was over $19 billion. Until we get some really good answers to these questions, I don't think we should be giving them that much money every year. And with $19 billion, you could easily fake this. It would be a lot easier it would be a lot more cost effective to fake this and have a lot more money left over than it would be to actually do it. So, until next time, think about all this. Peace.
Late December.
Hi, I'm Brian Mullins, and this is Balls Out Physics, episode 4.1, Virgin Galactic, Telecom, and Thermal Radiation. Now, I posted a link in the description below to a video called Space is Hard. It was made by my friend Droidfuel, who's spent a lot of time making videos about some of the stuff, some related things that I've been talking about, and he's also become a pretty good friend of mine. He also has a degree in engineering. We talk a lot, and we both see the same problems with the current model of our world, and so we've been working together a lot, and it's been a lot of fun. And so Space is Hard is all about Virgin Galactic and the struggle that Richard Branson and his company have had achieving low Earth orbit. He also made a video on gravity and the relativity issues, the history of it, and the holes that seem to be in the story, so to say. He spends a lot of time on these videos, so please watch his stuff. It's all pieced together with music and voiceover, and he spends a lot of time doing this, and he says it's a lot of work. And to be honest, it sounds like a lot more work than just standing up here and flapping my gums with a marker. So show him some love, please. Watch his videos; they're great. Need to motivate him to make some more because they're very good. Great talking points too. And they're usually only about 5 or 6 minutes long, so it's not something you have to sit and pay attention to for a while, like I'm sure my videos are. So anyway, back to his Space is Hard video. A couple of the key things I want to point out are, in 1999, Richard Branson announced Virgin Galactic, and it's a company to basically travel the stars eventually, and he announced shortly after the announcement of the company that the consumer or commercial flights tickets would be available to fly on commercial flights into low Earth orbit as soon as 2007, and that never happened. In fact, they've still never made it. They're having a lot of trouble achieving low Earth orbit, and that's kind of strange because in the late 50s. The Soviet Union was able to put a dog into orbit with no computers, no internet, no prior knowledge, no tons of aerospace engineers out there with experience, and Virgin Galactic can't do it. And then you can go farther and say in 1961, John F. Kennedy announced that we were going to go to the moon, and then 8 years later we did it once and then 5 more times, apparently. And I struggle with that one, but they went to the moon and came back. That is such a huge feat compared to achieving low Earth orbit. Low Earth orbit, or LEO, if you remember from the last video, is where is basically the thermosphere, and where satellites and the International Space Station and all these thousands of objects are supposed to be. And we've been shooting them up there all the time, and Virgin Galactic hasn't been able to do it in 16 years with the internet and all of this experience. Now you could say it's because they're using planes instead of using the ground launch pads, because SpaceX has been able to do it, but SpaceX has only worked with NASA so far and hasn't offered to bring any of us civilians up into space, which really is unfortunate because we really want to go. There's tons of people on this earth that want to go. Virgin Galactic's already sold a lot of tickets to some very wealthy people, and they still haven't been able to get any of them into space. So I'm struggling with this one as well. And so Droid Field actually recently enlightened me to this. I didn't even think about the connection between Virgin, or the misconnection, as you could call it. The how surprising it is that they haven't been able to get into low Earth orbit. And so I went to Virgin's website, and I found after a few clicks that they claim only 553 people have been into space. That's not a lot of people. 553 human beings ever. There's a lot of human beings in the world right now. That's a small amount of people. We have to trust them that they're telling us the truth about everything they've done. And the majority of them have all held some type of rank, commander, etc. So that means they signed a contract with the government. And some contracts that you sign with governments prevent you from telling the truth even if you want to. Now, that's speculation. I'm not saying that they're liars, but I have a lot of trouble believing that things are in low Earth orbit. So, just putting that out there. It's something to consider. It doesn't prove anything, but it is an issue. So, I also wanted to talk about telecom, and I will start with GPS. Not really telecom, but they are related. I probably mentioned it before, but GPS is one of the first things you think about when people would tell you that nobody's ever been to space, that satellites aren't real, and that satellites would burn up in the thermosphere, things like that. You say, well, how does GPS work? It's the very first thing I thought of. How does my Garmin work? That I don't use anymore thanks to cell phones, but it's supposed to work off of satellites, and I actually have an ATV that has GPS on it that worked way back in the early 2000s, and so I wonder, so that was one of the things I thought about too. How does that work? And when you really start to dive into all this and research the history of GPS, you'll find that during World War II, GPS was actually developed, and it went into service in 1947 before any satellite was launched. And so it actually worked using relay towers. And it could still be working the same way. That is a possibility. But the general consensus is that it works off of satellites. But there is a way it could work without them. And then that leads into, we had satellite phones in the 80s and the 90s. People, usually fairly wealthy people were using satellite phones. We had cell phones with towers too, but there were also satellite phones. They did exist. And then all of a sudden the mobile boom takes off, and well, actually I think they might have been all satellite, but anyway, the mobile boom takes off in the early 2000s and late 90s, early 2000s, and we start building towers everywhere. And a few years ago, I was doing a little bit of telecom work, as we call it, and companies will hire structural engineers the mobile providers hire structural engineers to analyze towers for putting more equipment on them. A lot of times, these companies are competing with each other so fiercely that they're trying to provide more bandwidth to their customers to grow their customer base. And so, they're putting more and more equipment, upgrading equipment, putting more loads on these towers, and to the point where we actually reinforce towers sometimes. The tower is maxed out with the amount of equipment it can support for wind loads and things like that. That they start reinforcing the base of the towers and the truss members and everything else, depending on what type of tower it is, to allow for more equipment. In some cases, they even build a new tower right next to an existing tower because we're trying to expand to all these mobile providers. But when I started thinking about this back then, I got into it. I thought it was really interesting at first. And the first thing that hit me is, why don't we just use satellites? We have to cut down all these trees. We have to build all these towers on Earth, and we launch all these satellites into space. There's so many up there. Couldn't we figure out a way to use them, or launch a few more? They seem to be so efficient. We have satellite TV, direct TV, stuff like that. So why are we building all these towers? If we're going to take TV into space, why wouldn't we take mobile phones into space, or the mobile phone service into space? It was very puzzling for me back then, but I just kind of shrugged it off, didn't really think too much of it. And then I got into other work where people are running fiber optic lines through cities to put more antennas up on the roofs of buildings. Just antennas all over the place. It just didn't add up for me, but I figured there must be a reason for it. But now I think that reason might be something else. I'm sure you know if you watched the last episode. So that was very puzzling for me. But in the last episode, in episode 4, I talked about conduction and convection, but I didn't talk about thermal radiation, and I didn't do that on purpose because I had looked into it, and I wanted to see what people said. I wanted to see what kind of rebuttals I got with black bodies and everything we're taught, how things radiate in space, and because I knew I had to talk about that in a separate episode because I wanted to explain the thermosphere and all that, and I didn't want to ramble on for an hour. So thermal radiation, I think the best place to start is how it works on Earth before you go into space to talk about it. And I want to start with an engine. I think this is the easiest way, a car engine, easiest way to explain it. Here I have an engine and a radiator, and for you gearheads out there, I'd imagine that this is a 4.0 liter straight 6 out of a Jeep. It's just what it looked like to me after I drew it. So we've got our radiator, we've got our hoses, our rubber hoses that transfers coolant to and from the engine, liquid cool. Almost all cars nowadays are liquid cooled, and so that's what antifreeze. You typically have a mixture of antifreeze and water in your radiator. Typically you just call it coolant. That if you fill your radiator and actually the fluid flows into the engine, and there's water jackets in the engine to allow the fluid to pass all through the engine and absorb heat through conduction, convection, whatever you want to call it, absorb the heat from the engine and then send it back into the radiator, where air, if you're driving, if you're moving, air is blowing through the front of the radiator, and the coolant's trickling down through little channels in the radiator, and the cooler air is passing through little slats. I'm going to draw like a front. If you look at it, if you're going to cut a section here, say this is a section looking at it, at the front of it, you would say section AA looks something like this. There's a bunch of little slits. Probably, if you've seen the front of a radiator, it's a lot better to look up a picture than what I'm drawing here. There's some little framing in here to hold all these slits together. The air passes through there, and the coolant, is draining down through the radiator, and the heat in the coolant is radiating out into the air. But you maybe call this convection, but it is a radiator, and then the heat is being transferred into the cooler air. So when you now have hotter air flowing through into the engine bay, however, since the coolant is since the engine is water cooled and there's so much cool water in the engine, it keeps the engine cool and keeping it from overheating. Now I forgot to mention there's a fan here, and usually on an engine that's orientated like this, which would be rear wheel drive, you've got a water pump that the engine belts turn, which I didn't draw, but that pumps the water through the engine into the radiator and back continuously. And the fan is usually mounted on the front of the water pump, and the fan is there so when you stop moving, you don't have air flowing through the radiator. There's a clutch in the fan, housing that has how the fan kicks on, or that grabs, and the fan starts spinning and it starts pulling air through the radiator to keep the engine cool while you're idling or sitting at a stoplight. That's basically how a radiator works. Okay, but I mean, even with the cooling going on, the engine still radiates what we call through infrared waves. This is what my FLIR camera measures. It still radiates heat away from it through the air, but not efficient enough so it'll overheat if it doesn't have a liquid cooled system. Now there are some air cooled engines that have just fans, but the engine does radiate some heat to its surrounding environment. Okay, so when you think about that, if you have a problem with your liquid cooling system and you say it's not working as well as it usually does, and it doesn't work so well that your engine might overheat, in what situation do you think it would overheat? Would it be more likely to overheat? Driving in the middle of the August summer heat, if you're north of the equator, or driving in the middle of January in the winter? Common sense tells you, obviously, it's going to be more likely to overheat in August, right? Because there's hotter, warmer air around it. And in January, there's colder, denser, more air, and it's cold around the engine. And if you remember from episode 4, hot goes to cold, so the heat and the greater the difference in temperatures, the faster it moves. So the more cold air there is for the heat to escape to. But you do have one more thing I want to mention is you have an engine compartment around the whole thing. So say here's your engine compartment. Goes back to the car, and there's a firewall here, something like that. And the engine compartment gets hot very quick. It fills up with that radiating heat. So I should have drawn it like this. It radiates out, and then the inside of the engine compartment gets pretty hot, and then everything starts to balance out. And so the liquid going through the engine is actually cooler and keeping the engine cold, and fresh air is coming in from outside the compartment to keep the engine cold. So if you have an old beater truck like me with a dated cooling system that you're too lazy to fix, sometimes you got to drive a couple hours on the highway in the summertime. What you can do is turn your fresh air intake on, open all your windows, and open up the heater vent. Turn the heater on, because the way the heater works is by blowing air, or blowing cabin air or fresh air across your coolant through a steel line or something, and that allows heat to come into the cabin. So when in the wintertime, this is how heating in cars works. So if you're ever overheating and you're on the highway and you don't want your engine to blow up, turn fresh air, turn the heater on. It works really, really well. So, if you got all the windows open in your car too, it's the same thing as the engine compartment. It lets the heat escape to the cooler air outside. It's still hot outside because it's summertime, but it's definitely a lot hotter in this engine compartment. So that's a way that you can save your car, your old truck. So that's to give you an idea of how it works on Earth. It does move through infrared radiation, but it's moving through air. The wave. If you imagine like waves in a pool, I still kind of visualize it as moving through the air in that wave, in that electromagnetic wave frequency. If you look at the frequency chart, so this is how radiation works on Earth. Now I'm going to cut and I'm going to draw a new sketch to try to visualize how this would work in space, or how I visualize this working in space, and you can form your own opinion on that. So I'll cut and be right back. Alright, so here's the new sketch. In the center here I have Earth that I sketched up based on the Apollo 17 photograph, which is probably the most famous real picture of Earth. What's very surprising when you start looking into all this is how few real pictures there actually are. All of the new stuff is composite. The new video Earth pictures is composite. You can really tell it's a composite, kind of almost like a rendering, or even cartoon some people call it. I don't want to call it that, or an animation for the newer stuff. And this was supposedly taken 40 years ago. And I've also watched people who are very good with Photoshop play with layers and break this down and show that it kind of looks like this was faked. But I'm not a Photoshop expert, and I'll let you be the judge of that. If you just look into this and see what you find. But anyway, assume it's real. Apollo 17 photo. We've got Africa, Madagascar, Saudi Arabia, Iran, and India up here. That's the footage that's in a lot of our textbooks, or the picture that's in a lot of our textbooks. And so I'm assuming that the sun is over here, and it's 100 times the diameter of Earth, so all of the light should be, or the majority of the light should be engulfing Earth, theoretically. And got sun rays, typical. TYP is a very common abbreviation you'll see on engineering drawings. So I've got the sun rays engulfing Earth, or absorbing the rays that are hitting it, and the other ones are passing by. The ISS up here in the thermosphere, and then I've got a blow-up of the ISS that I want to talk about, and also added up to Apollo 13 up here, because I've mentioned it on the last video, and some people had said that the light hits Apollo 13 and it heats up, but it immediately cools down, and immediately radiates away because of black bodies and thermal radiation in space through infrared light. Okay. So starting with the ISS, because the ISS does have a cooling system on it that's supposed to cool the what am I looking for? Solar panels. And so, you know, I'd kind of looked into that a little bit before I made episode 4, but you know, I figured I would get people commenting about that, about the ammonia-based cooling system. It's a liquid cooling system, just like I described with the engine. Well, not just like I described it, but very similar. And so what's supposed to happen is these are the solar panels right here. If you look this up, I have a link below in the description to a space.com article, or to the space.com description of how this works. And so you've got the solar panels, and then this is the body of the space station, and you've got Russian and American side. You can see all this on space.com. And there's supposed to be liquid ammonia flowing through the solar panels and through piping and everything that comes to these little red squiggly lines here that I've got representing the radiators. Now there's each one of these, there's 3 at each one of these locations, so there should be 6 radiators total. And so just like with the engine, the car engine, heat is absorbed by the solar panels to keep them cool. You know, heat escapes from the solar panels to keep them from getting too hot, and then the heat flows into the cooler ammonia, and then the ammonia flows to these radiators, and then heat radiates out into space, or the thermosphere where the ISS is. Okay, but in this case it's not the same, because the air particles are so far apart from the radiators that the heat isn't transferred directly into matter. In fact, the heat just becomes electromagnetic radiation or infrared light. That's very different. And what's confusing to me is when and why does heat suddenly jump from matter to nothingness? You know, we're told, and it's accepted, that light can travel through a vacuum. And we can build a glass vacuum tube or a box or something on Earth and apparently shine a light through it, artificial light that we create, and we can see the light passing through it. In my opinion, that's not the same thing. Outer space is not supposed to have a container, and I think the container does affect the experiment. And if you've ever studied the double slit experiment and what happens in that experiment, how do we know that we're not seeing light pass through a glass vacuum tube? Because we expect to see light beam, like covering all the electromagnetic spectrum, but we can see the visible light passing through it. Now that sounds far-fetched, and in episode 6 I will go over the double slit experiment, because that is one of the most mind-blowing things I've ever discovered in my life, and it'll help me explain why I think this could be different and possibly a trick, not necessarily people trying to trick us, maybe the world actually tricking us, and I'll get into that, so I can't explain it yet. So let's just assume it works. Let's just assume that heat contained in matter, in that ammonia, in the radiators, can just become infrared light and radiate out into space. And since space is so much colder, or the black bodies in space, because this is the theory, that there are black bodies in space that absorb all of this heat, or this electromagnetic radiation, it escapes from the station and it doesn't get hot. Okay? And my first question when I started thinking about this is, what about satellites? Do all of the satellites have these ammonia-based cooling systems too? Because they have solar panels as well. They're going to need to cool those solar panels. So maybe they do. But that's a lot of ammonia-based cooling systems. And have we been using those since we started launching satellites? I don't know. So that's the question there. And then Apollo 13, the argument against why it doesn't get hot is because the light hits it and then it immediately radiates away through. It immediately becomes infrared radiation. And the body of the space station is supposed to reflect that supposed to reflect electromagnetic light so it doesn't get hot, and the same with astronaut spacesuits, etc. That's a tough one for me, but assume it works. Okay? So, infrared radiation, or infrared light, radiates away from these little radiators out into the void of space, where theoretically I would say it's infinitely cold compared to everything else. It's theorized that out in space there might be locations where absolute zero is obtained. If you've never heard of this, absolute zero is the theorized temperature at which atoms stop moving. Things freeze completely. The electrons, protons, whatever, the stuff that makes up the atom stops moving. And that is roughly negative 273 degrees Celsius, or 0 Kelvin. We actually have a temperature scale based on this, and that's what Kelvin is. And if you want to convert Kelvin to Celsius, all you have to do is subtract 273 degrees from whatever temperature you have in Kelvin, and that'll be your temperature in Celsius. So just some food for thought there, and the idea of absolute zero, which we've never been able to attain on Earth through experimentation, but that makes sense because heat's always going to find its way to what we're working on somehow. But we have achieved some very, very cold temperatures, which is very interesting. So, all right, heat escapes these objects through infrared light. So it's not, the heat just becomes infrared light. That's the way I interpret it. And so here in the thermosphere, where we've got these hot temperatures, I crossed out sphere because I'm not sure what the Earth is, so I'm going to try to refer to these as the thermo layer, because layer works on a sphere or flat or concave, whatever. So then the thermo layer, even though the temperatures are this high, the particles are too far apart, so they don't transfer heat to the station, but they also don't transfer heat away from the station. So they're kind of doing nothing. And infrared light is doing it all. Right? And so somebody actually posted this on my last video. I looked through some PowerPoints, but I hadn't seen this one, and this one I like. It looks like it came from European Space Agency and a college course. But I've got a link posted this below, so you can go through the slide if you want to. And it's 66 slides, but I wanted to focus on radiation here. They go over the means of heat transfer, and then they state that radiation is how it's done in space. So we have the characteristics of radiation, propagation of electromagnetic energy in a straight line between surfaces separated by absorbing, scattering media, which they have crossed out because that's what happens on Earth with the engine example. That's what the air is around the engine. That's what it's considered, absorbing, scattering media. It absorbs the heat and scatters it out to colder areas of the air for heat to radiate away from the engine, or air traveling through the radiator, etc. But then they say it happens or in a vacuum. So in a vacuum, it also works, which is, it's two very different situations in my opinion, but it works in a vacuum. Okay. Hence, without matter displacement. So on Earth, we do have matter displacement with thermal radiation, but in space, we don't. It's totally different, which is somewhat confusing. Okay, and it's reflected, absorbed, or transmitted on surrounding bodies. And so in space, what they do is they assume this idea of a black body is either real or a fictitious surface. So, and my guess is it's generally fictitious because they don't have an actual body they can use for analysis, but it's real or fictitious, and it absorbs all incident radiant energy from every direction at every wavelength. Okay? And so radiated energy depends only on temperature. See that? So that's how it's supposed to work in space. Well, the thing is, we can't test this. The majority of us human beings here on Earth, only 553 people have been able to witness this in action, allegedly. So we have to take their word for it. We can test the car engine, as everyone knows car engines get warm, and you can see coolant flowing through a radiator if you open the cap on a radiator. Now, only do this if the engine is cool or running at operating temperature and not overheating. Never ever open the cap on a radiator if the car is overheating. You may be tempted to do that to cool it down, but you will get burned. And I was stupid and did it once, and I'm very lucky that I didn't get very badly burned from it. I was very young and naive. But don't ever, just if the engine's warm, just don't open the cap. But you can see coolant flow through a radiator, and you can feel heat from an engine. And if you open the hood of an engine compartment, you can feel the heat rush out into the cooler air that's around you. And you can also test cooling an overheating engine with a heater by turning the heater on if you want to. These things work. We know they work. So we can test this on Earth. We can't test this. We can't test electromagnetic radiation, light, hitting objects in space and then immediately radiating off so they don't melt. Okay? We have to take people's word for it. And it's hard to wrap your head around because it seems to be opposite of what happens on Earth. It seems like as I explained in the engine example, on a colder day, an engine would be less likely to overheat. But the temperature in the thermosphere is 1,500, 2,000 degrees Celsius. So that's what's strange here is the IR light, infrared light, is unaffected by the temperature of the thermosphere. It doesn't matter. It's all about black bodies and how the radiation wants to travel to these fictitious black bodies that are very cold. Okay? So that's how it works, and let's assume that it does work, that the electromagnetic or the infrared light can transfer heat away from bodies in space. Alright, so now that we went over the space station, get rid of that, I had that blown up view of it. So Apollo radiates away its heat. We know that, that's what we're assuming, that it works. ISS radiates away its heat. So now, you might be wondering, like I am, what about Earth? Earth, we're told, as I explained in episode 4, Earth gets warm because the atmosphere, the particles in the atmosphere, the air, absorbs light, electromagnetic radiation from the sun and becomes warm. That heats it, okay? So, light is coming from the sun and hitting this side of the Earth, and it's being warmed, right? And as we know, when the sun goes down, or goes out of our view, whatever you want to call it, the air begins to cool, the ambient temperature begins to drop. And so that would be this side of the Earth. It would be nighttime on this side of the Earth. But if actually, I'll put that back up here. If all this heat right now is radiating away from this Apollo 13 or any other spacecraft or a satellite that's in space, then why doesn't it happen to Earth? Once this side of Earth is no longer in the sunlight, shouldn't all of the heat immediately radiate away, just like it does for objects in space? Remember, when we look at the layers of the air, start down here in the troposphere, this is where it's cooling off, where we experience the temperature drop at nighttime. When you go into the stratosphere, the temperature does go up a little bit, but it doesn't get higher than it does in the troposphere, and then in the mesosphere it gets colder. So thermal radiation, from the engine example, you would expect heat to move up into the mesosphere, but then it gets really hot in the thermosphere, so you would expect it to move into these colder layers here and not go into the thermosphere, unless you accept that, or you take the assumption that the thermosphere doesn't affect thermal radiation. Now there's a gray area there, because through these layers it's moving through air, and the wave, the electromagnetic wave, is moving through air, and so air is kind of part of the wave. It's scattered. It's scattering meteor. There's matter displacement, as shown in that PowerPoint slide. But since in the thermosphere the hot air doesn't affect the satellites and the ISS, we have to assume that it doesn't affect thermal radiation leaving Earth, or radiated heat leaving Earth, right? It has to be that it can't do one and it can't stop one and it can't stop one and prevent one and allow the other to happen. It has to be consistent. I mean, at least that's what logic tells me. So thermal radiation leaving the Earth is not affected by the thermosphere at all. So what stops all of this heat from immediately escaping? And these fictitious black bodies are very, very cold in space, and we assume that there's very, very cold mass out there in space, and that all of these objects up here, the ISS, the Apollo capsules, whatever, space shuttles, everything immediately radiates the heat away so it doesn't overheat. So wouldn't that happen here on this side of Earth? What's stopping it? Why all of this heat would immediately radiate out of space? This side of Earth would freeze. We'd die. We couldn't survive here if this is what happened. That's just the way I see this, looking at it logically. I mean, even if you make a fire, that heat is gone. It's just immediately, without the sun there warming the atmosphere, we would get very, very cold, just like everything else, right? Just like all the other objects in space. This should all happen the same way. That's very puzzling, because we know one thing we can test is we can go outside at night, and yeah, it's colder, but we don't freeze to death. I mean, in certain parts of the world it's probably pretty cold, but we can put coats on and we can survive. But the ISS, according to NASA, without its ammonia-based cooling system, would see temperature swings between 250 degrees Celsius and or Fahrenheit and minus 250 degrees Fahrenheit. I think it's around 150 degrees Celsius, well over the boiling point of water, and minus 157 degrees Celsius. I said 150 and minus 157, something like that. It's very huge temperature swings. But with their heating and cooling system, it's controlled. But Earth doesn't have an ammonia-based heating and cooling system. It's just got air around it. And so what keeps all this heat from escaping? You might think, when I first started thinking about this, I thought, okay, maybe some of this heat from over here where it's getting hit by sunlight makes its way over here. But no, space is colder. The assumed black bodies in space are cold. So the heat would be going this way too. It wouldn't come over to this area. I mean, the heat would just be trying to get away from Earth as fast as it possibly can. So that doesn't make sense to me. So what are we left to assume here? We know it does cool down at night, but not as rapidly as the rest of these alleged objects in space, these alleged satellites. Where's the heat going? That's the question. Well, if you've been following around with my other videos that I made in between episode 4 and this one, then we, the truth-seeking community, this amazing community of people asking questions and working together to try to find the truth for no other reason than to find the truth. Sorry, I'm very excited about that. It's so awesome. But we may have come to a conclusion of where it's going, and I'll talk about that in episode 4.2. So think about this. Where is this heat going? Now, one more thing I want to say, because I still don't, there might be an explanation out there for this, but I like to try to think things through on my own. Why does heat that's contained in matter suddenly jump to electromagnetic radiation, infrared light, where there's no mass? Like we said, infrared electromagnetic radiation can travel through a vacuum. We're assuming that is correct. But what makes it jump? And when I really started thinking about this, I remembered the most, I'm sure you've seen this equation before, the most famous equation that we've all heard of, I'm sure, is E equals mc squared. I'm sure you've heard of this equation, right? Everybody's heard of this. What this says is energy, or heat, or the amount of energy contained within a unit volume is actually the definition of heat. People have called me out on that, and temperature is actually the measure of energy in the particles, but semantics, in my opinion. Heat, energy, is equal to mass times the speed of light squared. But we have energy moving through nothing, and there's no mass, because light doesn't have a mass, or sometimes they say photons do have mass, they don't have mass, do they? I don't know, but infrared radiation, does it have mass? But there's no particles in the thermosphere, and as you get into the exosphere and out into space and farther away from Earth, there's very, very few particles, not enough for waves to travel through, so the waves are traveling through nothing, because here on Earth, when electromagnetic waves travel through the air, it's kind of like waves traveling through a pool. Like, you can't see it, but they are moving, they're displacing matter. Matter is being affected by the waves traveling through them. But in space there is no mass. So if mass, isn't mass zero? This becomes zero. 0 times something is always 0. So energy is 0. So heat's 0, well, what? Very confusing. I'm sure there's probably a complicated explanation for this, but this is very simple math here. This equation is very well accepted, especially when it comes to nuclear power. So, what's going on? How can things in space be so different than on Earth? And what I always go back to, yet we theorize dark energy because of the conservation of angular momentum, which we've tested and shown works on Earth. But then some of our laws seem to get defied right around Earth, and it just doesn't add up for me. And so this is why thermal radiation and black bodies and all of this kind of complicated reasoning isn't logical to me. This equation was thought up by Albert Einstein. Most people know that. And Albert Einstein said that if you can't explain something simply, then you don't understand it well enough. Well, the general public, the people that are paying for all of this space travel, all these satellites, we're the ones paying for this. We are asking for explanations for these things that don't make sense for us. And we don't want complicated explanations, and the man who came up with this equation, the unofficial poster boy of science, in my opinion, everybody knows who Albert Einstein is. He's probably the first scientist you think of when you say, hey, name a famous scientist. He said that if you can't explain something simply, then you don't understand it well enough. So we need some simple explanations for this. We're tired of complicated explanations. A lot of people haven't had all the math that these scientists have had, and I mean engineers and everybody else. I mean, you're throwing out equations with derivatives and integrals and I mean, all kinds of calculus, and it just confuses people. They don't want to try to figure out the answer that way. And if you have to explain it with calculus, then you don't understand it well enough. I think. I agree with Einstein on that one. So we have, again, 553 people to trust, the majority of whom sign contracts with governments, and how can we trust that they're telling us the truth? Many people aren't trusting government anymore, and I don't trust the government very much. One of my favorite memes out there is those who trust the government probably didn't pay attention in history class, because governments have done some very bad things to people over the years, and they're pretty much responsible for more death and poverty and suffering than anything else. So why are we trusting government agencies to tell us what our world is? I don't know. Getting too philosophical, I guess. But these are the things I'm struggling with, and this one defines so many simple things, simple equations, simple logical thoughts and reasoning. So think about it, form your own opinion, because this is just my opinion. I'm just giving it to you. I'm not telling you what's true or not, like I try to say a lot. So that's it. Can these things really cool in space, or cool instantly in space, without it happening to Earth too? And if this isn't what's keeping Earth cool, if this thermosphere is really hot and it would affect thermal radiation, then it would keep all the heat in. So then where would the heat go? The heat wouldn't be able to escape, and then these layers would get really hot. I mean, just thinking about this, if the sun is constantly heating the Earth, the heat wouldn't be able to escape. So we would all catch fire, and I mean, the whole Earth would burn up. The heat's got to go somewhere, and that's what we'll talk about in episode 4.2. So, until next time, keep thinking, keep asking questions. Let's find the truth. Peace.
But you can't read my hand.
Hi, I'm Brian Mullins, and this is Balls Out Physics, Episode 5, Propulsion in Space. Now, a lot of people out there, including myself, when they started questioning things, questioning space travel, start to think about how in space there's nothing, or there's no matter in space. And a lot of people have said, well, what are you pushing off of in space? And that's one of the things I started to think about a lot. And it's one of the things that kind of broke my heart, because if you watched episode 4, when I talked about the thermosphere, I realized that the temperatures in low Earth orbit were too high, but I did wonder if we can get through the thermosphere, can we still travel the stars? But then I started to think about this idea of having nothing to push off of, and I realized that I don't think it's even possible to move in space if it is what mainstream science or mainstream astronomy believe, that it is a vacuum. It shouldn't. You start to think that it shouldn't be possible to move, and I thought of Newton's third law, which basically says that every action has an equal and opposite reaction, and that's definitely true on Earth. If you push on something, it pushes back with the same force, or pushes back. It creates an equal and opposite reaction. Eventually it will. If you push on something that's not strong enough to resist your force, then you'll move, or it will move, until enough force is developed until enough reaction is developed to resist your force. So, for example, if I crouch and then push up on the bottom of my feet to push myself back up, that the reaction of the floor pushing back up is equal to the force of my feet pushing down. That's basically what Newton's third law says. Okay, so a lot of people say, well, in space, how can you move when you've got nothing to push off of? And what we're told, what the accepted theory is that if all you have to do is push mass away from you, and you'll move in space, and it kind of makes sense, but then Newton's third law comes back, and so there's a lot of circular reasoning for me trying to figure this out. Like, what am I missing? Because I didn't want to accept that you can't move in space, but I honestly don't think you can. But start with a jet engine on Earth. Now, on Earth, we have air all around us. It's a fluid, really, and it's not that much different from water when you really start to think about it. Gas and liquid are very, very similar. They're both fluids. And so, say this is a jet engine, a very crude drawing of a jet engine on a commercial airliner. And when I'm standing here, where you're standing at sea level, the pressure on your body from the atmosphere, the weight of the atmosphere above you, is roughly around 14.7 pounds per square inch, or 101 kilopascals if you're using the metric system. And so really what's creating that pressure is the weight of the air above you, all of the air above you. It's just like the best way to think about it is that if you dive in a pool and you swim to the bottom, you can feel the pressure increase as you go lower and lower in the pool. That's because the weight of the water above you is increasing, and you really feel it in your ears. Especially if your ears are very sensitive, you go lower and lower, you go deeper and deeper. You go, depending on how deep the pool is, you feel that pressure in your ears. It's the same thing in the air, just not as noticeable. And so, as you rise in a pool, the pressure becomes less. And the same thing happens in our air. If you go up into the mountains, the pressure actually decreases, and you have to. And when engineers are designing things that are affected by pressure, they do account for altitude and how pressure changes. And at sea level, we use 14.7, and that's typically called 1 atmosphere of pressure. Okay, so a jet engine sitting here, say the engine sitting on the runway, is experiencing this pressure all around it, just like our bodies are. And that's one of the reasons it's theorized that you need a spacesuit in space. One of the reasons is because our bodies in space would expand because space has negative pressure. And so, the atmospheric pressure is what actually holds our bodies together on Earth. That's the theory. So you have all this, call this the air pressure, this atmospheric pressure, if we want to call it that, or whatever, is acting on this engine from all sides. Okay, as it's sitting here on the runway, just like it's acting on my body, it's acting on you, the viewer, and everything. Okay, so there's pressure here. And that is 1 ATM equals 14.7 psi. I'm going to use English units because that's what I'm used to. But I do think the metric system is better because, well, I think if you do believe that this world was designed, I think the designer gave us a hint on which system is better. It's just easier for our heads, but each their own. So, okay, have an engine sitting here. It's off. All right. I posted a link below to a 5-minute video that shows how a jet engine works in a nutshell, and it's very cool how they work. It's very interesting. It's really based on how a nozzle works. So to give you a good example, that you take a garden hose and you turn the hose on full, and water streams out of the end of the hose. But if you put your thumb over the end of the hose and cover, say, half of it, the water sprays out much faster. And the reason that happens, it sprays out faster and farther, is because you increase the energy, but the amount of mass flowing through stays the same. You think about it, behind your finger, there's still the same amount of mass, the same amount of water is flowing. But then you reduce the size of the hole that the water can come out of, but that same amount of mass still has to keep moving because there's still that much mass behind it, pushing it. So that's why the water sprays farther and faster, because you're actually increasing the energy. And if you think about it, kinetic energy is equal to, KE is equal to 1/2 mass times velocity squared. So you see what happens here is the velocity increases because you reduce the area, and so your energy increases. Now, I could get into the flow equation and show how when you actually reduce the area, it increases the energy, but I'm just giving the basics here. This is what's happening. And that's how a jet engine works too. in a nutshell. There's a little more complicated than that, but what happens is the intake in the front of the engine, where the fan is, if you see you see the front of a jet airliner, it has a fan here, and so fan turns on, and these things really suck an enormous amount of air into them. Okay, they suck in this air, as you see in the shape of the engine. If you watch that video, about 80% of the air just flows around the turbine in the center. And so, just to keep it simple, we just say that the air comes in a big opening and then comes out of a smaller opening, so it's forced out the back at a higher velocity. The energy is increased. Okay, keep it simple. So we'll just use here for this. So this air is forced. This air is forced out the back. Now, this little turbine, this cone represents the turbine, and there is some difference. About 80% of the thrust comes from the air flowing through, and then about 15 to 20% of the thrust comes out of the turbine. But for this, we'll just say it all. It's the thrust is being forced out of the back of the engine. Okay, and so per Newton's third law, every action has an equal and opposite reaction. So this thrust creates a reaction on the engine. I'll just put it right here. Call this the reaction R, and pushes the jet, and eventually pushes the jet forward. That's not the only action happening here. The typical example, or the classical example, is that the thrust pushes this way. The action of the thrust pushes this way, creates a reaction to push the rocket. Okay, but there's something else happening here. There's a lot of actions happening. The thrust is acting on the environment, or the air is acting on the thrust, however you want to look at it. So the way I see it is it's like this column of air, this jet of air is being sprayed out of the back of the engine, and you have this atmospheric pressure that's pushing the surrounding relatively stationary air against it, or holding it against it. So we develop little reactions, friction between the air. This is kind of like the viscosity of a liquid. Actually, it's pretty much what it is. So little shears, as I call it. And that's how you develop the reaction between the thrust and the air. Does that make sense? So like the pressure holds the stationary air, relatively stationary air, against the thrust, and that creates friction, which creates a reaction against the thrust, which basically you have to keep your action reaction going to move. Make sense? So that's how it works in a nutshell on Earth. There's a lot more to it, but watch that video to understand how the jet engine works. Okay, but in space, it's different. Space sucks. Literally, it sucks. It's a vacuum. The pressure is negative. So all these blue arrows pointing at the engine would be different. So just they'd be facing the other way, because space would be sucking on the engine. Now a jet engine like this can't work in space because you need an intake. You need to pull air in and force it out the back. So that's not how propulsion in space works. And when I was a kid, I grew up watching the space shuttle launches, and I was quite obsessed with it. I wanted to be an astronaut like every kid for a little while. And I liked watching how it moved. I liked learning how it worked in space. And if you remember the space shuttle program, the way the space shuttle worked after the launch, after it got into space, it had these little jets. It had these little jets all over it that shot compressed oxygen out into space, and that was supposed to be the mass moving, the push of the mass away from the mass of the oxygen away from the shuttle was supposed to be what controlled its movement and gave it thrust when it needed to, and rolled whatever it needed to do. The little tss you see in the movies. Well, so let's say that this is actually one of the little nozzles on the shuttle, okay? And then we'll extend the nozzle over to the shuttle. Say the shuttle's over here somewhere. This is just one of those little nozzles, tiny little nozzle that shoots compressed oxygen out into space, okay? And remember though, space sucks. So you have this pressure acting the other way. what that pressure is really not important because it sucks. That's all that matters. I'm being so we have all this suction happening on the engine, and and on the, or not on the engine, on the nozzle, excuse me, and it's pulling on here and say the nozzle's closed right now. This nozzle isn't active yet, and so you have this built-up compressed oxygen inside this nozzle, and say there's a tank over here filled with compressed oxygen, and when they open the end of the nozzle, or the jet, whatever you want to call it, you have this suction force over here, and then I'll use red to show that the very high pressure oxygen wants to spray out into space. But space is already pulling away from that oxygen. So how do you develop an equal and opposite reaction when space is already pulling all of this stuff away? It's sucking, it's pulling. So this opens, and there's compressed, built up oxygen in here, and the oxygen is actually pushing on the wall of the nozzle and the tank that it's in. Okay? It's already pushing on that surface. And then it opens and it sprays out into space, but there's no air out there. There's no positive pressure to hold air against the oxygen if there was any air. And so it would just, in my opinion, I mean, when you really start to think of it, wouldn't it just expand infinitely the moment it starts to come out? Where's the opposite reaction created? And that's what people are really asking. Our guts, that's like a lot of people, our gut reaction is, no, wait, that doesn't seem like it would work. And so this question is discussed. I actually have a friend who took a propulsion class. I can't remember what the class was called. He took it was an online class. It was free from a very well-respected university. I won't mention it. Well, it was MIT. But they offer free courses, and he told me that in the course that to answer this question, what they do is they show the professor has a video of himself standing on a skateboard, and he took some weights and throws the weights away from him, and he moved back the other way. And I said, oh, I got to try this. And so I took I had an old skateboard, and I went out into the garage and I started throwing weights away from me, and I didn't move. And I was like, they can't lie about something like that. That would be, people would test that eventually, right? Come on. And so I may have said this in the past that I didn't move on the skateboard. So the skateboard had really old wheels on it, and these are the wheels that used to be on it. You can see the bearings are kind of rusty. And so I decided I really need to do this right. So I got some nice rollerblade wheels. When I was a kid, it was considered lame to put rollerblade wheels on your skateboard, but I kind of sucked at skating, so I just liked going fast. And this skateboard is the design here. My idea here is for this thing to only go straight. Because you see, if I try to turn, the board will hit the rollerblade. But so I got some new bearings. Wheels spin really well, and I set up a trap or something to catch stuff as I threw it away from me. And I stood on the skateboard and started throwing mass away from me. Well, I took a cinder block or a CMU block and threw it away from me, and sure enough, I moved backwards pretty significantly. So I was like, okay, that works. But is that the same thing? Well, it took me a while to wrap my head around it. I'm like, where's the equal and opposite reaction? And is this the same thing? And I don't think it is. And here's why. Best way to think about it, let's start with a bullet. Okay? Here's a bullet, all right? With a bullet, you have a brass casing, and you have, this is actually considered the bullet, and this is the casing, or the cartridge, right? The brass casing. And this right here is the joint between the two of them, okay? And on the back, you have a primer, this little circle here, and the firing pin strikes the primer and ignites the gunpowder within the cartridge, and the gunpowder explodes, and it pushes in all directions. But since this bullet, since there's a seal here, and this is the weakest point between these two masses, the bullet flies one way and the casing tries to fly back the other way. If you've ever shot a gun before, if you're holding a rifle against your shoulder, you get a kickback, but the smaller mass of the bullet's mass is much smaller than you, the rifle, and the casing, so the bullet flies away from you. And so one of the when people ask this question, when I asked this question, one of the things I got was, well, if you put a bullet in a vacuum chamber or in space, and or a gun, and you were able to strike the primer, and there was oxygen contained, and say the bullet was completely sealed, the bullet and the gun would fly away from each other. I said, yeah, it would, because you have two masses with an action happening between them, so you get two reactions there. Does that make sense? And so I started thinking about that, and I said, well, a skateboard's the same thing, really, as the bullet. The action is my arms, or the professor's arms, pushing on that mass, and the reaction is occurring between the action of your arms on you and the on me and the CMU block or the tire that I threw, or whatever, or the weights, whatever you throw. You actually create two reactions there. Okay, there's an action between them, but here it's not the same. Before, in my opinion, it's not the same. Before the shuttle leaves the Earth, they fill the oxygen containers with oxygen, and the nozzles and everything with oxygen, and it becomes pressurized. The oxygen is forced into the container, and the oxygen expands. High pressure pushes on the outside of the container, and then the container pushes back against these little pressures that I show here. The container pushes back, so the action and reaction has already occurred. Okay? And it's just waiting there, and this is now potential energy waiting to be released. So the action and reaction has already occurred. This isn't the same thing as somebody standing on a skateboard and throwing something away from him, or a bullet. It's not the same, in my opinion. I mean, really think about it. You see what I'm saying here? You need two masses with an action happening between them to move in space. On Earth, this nozzle would spray against the air, and you would get an equal and opposite reaction, because there's positive pressure on Earth and there's air. In space, there's not. It's completely the opposite. It's just like, it's very similar to the jet engine on Earth, except you don't have the intake, you just have compressed oxygen spraying out against the air. In space, it's not the same. And I don't think it works. It's kind of hard to wrap your head around this one, but what's amazing is so many people have this gut reaction, like, yeah, that shouldn't work. And I had a hard time trying to wrap my head around why my gut was telling me it didn't work. And it's pretty amazing that we have that ability to know something's not right. We can feel it, but we can't actually get our minds to see right away what the problem is. I find that very interesting, because statistically, with multiple choice exams, when someone comes to a question that they don't know the answer to right away, your gut reaction, your first instinct, if you have four choices, a multiple choice test, A, B, C, or D, your gut reaction, the first one you see that looks good, usually is the right answer. It's pretty amazing. It's sometimes called intuition, and women are known for having better intuition than men. So, ladies out there, how does this feel? What do you think about this? Does this make sense? Does it seem like we should be able to move in space with this type of propulsion? Now, if you had a bunch of bullets and and barrels sticking out of the space shuttle, and fired bullets out of those barrels, then I would think you would be able to move for the reason I explained. But carrying bullets and gunpowder up into space, first of all, it's really heavy. Bullets are heavy. Lead, for one, brass casings, gunpowder, everything. And all the high temperatures you're seeing up there, and the high pressures and everything, and these extremely flammable bullets, have fun with that. I wouldn't do that, and I'm sure nobody would want to do that. So you would need two masses and an action happening between them to move in space. Whereas in this case, you only have one mass that's already contained, it's already pressurized, the action and reaction has already happened, and then when you open the nozzle, it just sprays out into space. Make sense? So that's the problem I see, and today is April 1st, so I kind of figured out how to explain this. Droidfield and I were actually talking about this one, and then it kind of worked out that what we both see. A lot of people feel that something's wrong about propulsion in space, or the way that the classical ways we've been taught with compressed oxygen being sprayed out into space, and that was how the shuttle moved. I know there's different propulsion systems out there, but space shuttle was supposed to exist and it was supposed to move up there, and a lot of people are thinking that it wasn't real. And based on everything I've shown in episode 4 and what I've seen, all the hoax footage, I don't think it's real, unfortunately. And so had to cut. So yeah, as I was saying, today's April 1st, and I think we're all being fooled by these space agencies, and there are a lot of people who agree with me. I mean, it's the number seems to be growing more and more every day. There's in the description below, I posted another link to a video showing glitches and anomalies and things that don't look real on the space station, that was made by a person who actually who does think that we live on a globe. I remain open. I have no idea what this world is at the moment, and I'm trying to determine that, so keep reiterating that. And so yeah, I think we're being fooled. Another thing I want to point out is if you watched episode 4, there's two episodes up right now. There's probably more sub-episodes for episode 4. I talked a lot about the International Space Station and the temperatures and all the problems with low Earth orbit. But the International Space Station is supposed to have an ion thruster on it, and it seems very high tech. I've looked into it a little bit, but I don't really want to spend too much time trying to understand how it works, because if the compressed oxygen propulsion has problems, I mean, what's the point really is how I feel about it now. But the reason that the ISS has an ion thruster is NASA says is because the space station runs into gas particles in the thermosphere. There's collisions with gas particles that are significant enough to slow it down. And if you watched episode 3, in episode 3, I talk about how the minimum velocity, or the velocity at whatever altitude is calculated to, or a minimum velocity that you need to maintain to stay in orbit, so you don't get pulled towards the Earth or whatever object you're orbiting. And so the space station has to maintain that minimum velocity, or it will get pulled towards Earth. If it increases the velocity, then based on the heliocentric model and our gravity equations, then it would move farther away from Earth. So they have to activate the thruster every 3-6 months, I don't remember what it is, due to collisions with these gas particles. So if you watched episode 4, the whole episode was all about, how come this station doesn't get hot? How come satellites don't get hot? And so these collisions with particles are significant enough to slow the station down, but not significant enough to heat it up, because the particles contain a lot of energy. It's very hot up there. So there's a lot of contradictions, a lot of things that don't make sense. And then when you see video, when you see things that show glitches and makes it look, just anomalies that look fake, pay close attention. That video, the first time I watched the video I posted down below, I didn't really see a whole lot, and then I really started paying attention to what the video creator was actually trying to show. I said, wow, yeah, there's things that it does look fake, like it's been faked, or it's pieced together, or like they're in a pool. So I'll let you be the judge of that. I'm not telling you what to believe. Like I said, this is my opinion, but there are people out there who agree with me. It's a lot of people are agreeing with me, and I'm agreeing with others who are doing work like this. So we need some answers, and we're paying for all this stuff, and when still only 553 people have been to space. So we need to stop paying to be fooled, I think, if we are being fooled. And at the moment, I have to conclude that. So, regardless of the shape of the world, I'm going in kind of a different direction as well. I'm going to keep making Balls Out Physics episodes, but I'm also, besides what the shape of this world is, I'm kind of leaning towards trying to understand how it works. And if these space agencies are going through all this trouble to fool us, maybe it's because they do know how this world works. Could be. Or could not be. There could be logical explanations for all this stuff, but that's why I'm making these videos, to see if we can find them or see if we can't. So, until next time, peace. Hi, I'm Brian Mullins, and this is Balls Out Physics, episode 5.1, Propulsion in a Vacuum Chamber. Now, in the last episode, in episode 5, I stated that space sucks, and a lot of people said that that's not true. And I made this video to kind of explain why I think that is true, or would be true if it exists as we've been taught, and why it would be different from a vacuum chamber that we would construct on Earth. And so I started working or thinking about how a vacuum container would be constructed, and thankfully somebody had already messaged me about some experiments he had been doing on his own with CO2 cartridges. So I have to say thank you, Rob, for giving me this idea. But I thought about a CO2 cartridge, and the CO2 cartridge somehow suspended in a chamber, in a vacuum chamber like this. I've got the CO2 cartridge, as you can see I traced it, suspended from a string, and the idea would be that we suspend it from a string because we have to deal with weight on Earth, and we'd rig up something, which is this little green line here, some kind of pin that would rotate and puncture the end of the CO2 cartridge. Okay, and that would spray the contents of the CO2 cartridge out, and we'd be able to test whether it works or not. But thinking about how a CO2 cartridge works. Right now in this CO2 cartridge there is compressed carbon dioxide, and the carbon dioxide, the compressed gas, is pushing on the inside of the container, kind of like I showed in the last video with the compressed oxygen. Okay, but at the same time the air pressure, the 14.7 psi that I also pointed out was considered atmospheric pressure, is pushing back on the container. So the net difference between the CO2 pushing on the inside of the container and the atmospheric pressure, or the air pressure pushing on the outside of the container, is how you determine what force is on the actual container. And then the container has to be strong enough to resist that force, or it would rupture. And so since if you puncture the end of this CO2 cartridge, all the CO2 is going to come flying out. If you had it in your fingers, it would want to shoot out of your fingers, right? And I believe that's because, yes, the thrust is creating a reaction on the CO2 cartridge and pushing it, but also the CO2 is pushing against the air, and the air is pushing back. Okay? Whereas in a vacuum, I don't think you would have that. But then you've also got the vacuum chamber to construct, and that is basically done in the exact opposite way. Okay, so you have this vacuum chamber that I just drew as a big box here. I actually got this idea from watching something Mythbusters did, and you'd have to have a pump on it to suck all the air out. Now, to visualize how that would work in reverse, you can just use a bottle. Okay, no jokes about this, but when you go to suck the air out of the bottle, you're sucking the air out, which is pulling on the inside of the walls, and the atmospheric pressure is also pushing on the outer wall. So when you suck, collapses, right? So you have to build this chamber to be strong enough to resist that outside pressure pushing on the walls. Excuse me, I should think all the force is from the outside pressure pushing in. When you try to suck it in, that's when you really experience the air, the weight of the air, or the pressure of the air on the outside of the container, because you're pulling the pressure out from the inside, creating the pressure differential. All right, and so this is why I think that space sucks, because space doesn't have a container. As it's theorized, our universe, as we've been taught, is supposed to be expanding infinitely. It never stops expanding. So space always has more space to expand into. So any propulsion that's sprayed out into space is just going to expand infinitely with the rest of space. There's no way for pressure to develop. See what I'm saying? And so to create this vacuum chamber, the first thing you would do before you run the experiment is turn on the pump to suck all the air out. Okay, so all the air
in the container gets sucked out. Okay. Now the air rushing past the CO2 cartridge, which would, if we're hanging it from a string like I have here, would probably get it moving, rocking back and forth. So after all of the air is sucked out of the vacuum chamber, and assuming these walls are strong enough to resist the air pressure that is pushing on it from the outside, then we now have a vacuum chamber with zero pressure, not negative pressure, or like I said in episode 5, or that not a constant sucking pressure. Once the pump kicks off and you don't have any stuff or any air left inside the vacuum chamber, then you just have this positive pressure pushing on the wall, and the pressure in here is essentially zero. Okay, so if you were to puncture the side of the tank, the pressure differential would make since there's zero pressure in here, and out here the pressure is P ATM equals 14.7 psi. Since you have that pressure out there, all the air is going to want to rush into the vacuum chamber. Okay, so suck all the air out. All right, turn the pump on, suck all the air out. Okay, CO2 cartridge stops swinging. This is just one idea. There's probably better ways to support this, or other ways to support it, because this does create a problem, which I'll show in a second. But okay, air's out of it. There's zero pressure inside the tank. Use this blue marker for pressure. Dropped my bottle over there. So P ATM or pre PC for chamber equals 0. Right now. Okay, so we've got this little pin rigged up somehow. Either if it's activated wirelessly, that would be a good test to see if electromagnetic waves can pass through the wall of the container and continue passing through the vacuum, or maybe we have some kind of wire hooked up to this string to activate it through a wired connection. So this little pin flings down and punctures the CO2 cartridge, and then bounces back out of the way. We designed it to do something, and then immediately this high energy CO2 sprays out because you have so much pressure inside of the cartridge. Now the pump's off, but this is sealed. Immediately this chamber begins to pressurize, because remember, there was no air in it before, so now this is no longer the case. Immediately pressure builds in the chamber from the propellant. So now basically what's happening is the CO2 expands out and bounces off of the walls, and then creates the reaction that we need to push on this CO2 cartridge. So in my opinion, building a vacuum chamber on Earth isn't the same thing. I don't think we can build a vacuum chamber on Earth that would simulate what outer space is supposed to be, as we've been taught. But I did think about it a little more, and I said, okay, well, could we do this? In order to simulate space, infinitely expanding away from itself, or the universe infinitely expanding away, what we could do is have this pump timed or linked to this pin, so that at the moment that this pin strikes the CO2, this pump comes on and evacuates or sucks out the propellant at the same rate at which it comes out of the CO2 cartridge. We could figure out how fast and how much CO2 comes out in a set amount of time. And so the pump kicks on right when this pin hits, and so the propellant sprays out, and then of course gets sucked right out by the pump, right? And then gets sprayed out into the air or the surrounding environment. And that, in my opinion, would somewhat simulate what we've been taught outer space is. But that, in my opinion, would make it so this won't move. Now, theoretically it wouldn't move. I mean, this would have to be timed perfectly to simulate outer space. And so, assuming this doesn't move, I mean, it might get cold a little bit. I mean, there's a lot happening, and we have to assume that the pump can suck all of that CO2 out. And you kind of see where I'm going with this, where we're eliminating the ability to create a reaction.
But that's what we would have to do to simulate space, in my opinion, just after really thinking about this. But the other problem here is, once this, if you do gain some thrust, say we don't have the pump on, this string, once it moves here, once it's a terrible CO2 cartridge drawing, but you see what I'm saying? Once it moves up here, now we have weight pulling down against the thrust. So a string might not be the best way to do this. There might be better ways, but that's the other problem. On Earth, we have to deal with weight, whereas in space, as it's theorized, it's weightless, so we don't have that problem. Okay? So this is why I say space sucks, because it does not have a container. Okay? So another thing I was thinking about, though, is to go back to the action-reaction. If you've got this set up to do this and it works and you get no movement in here as we should expect, okay, based on action-reaction, now you have a force, you have this propellant being ejected from this pump, which is pushing on the container. So just to keep, stay in the spirit of Newton's third law and action-reaction, now there's a force pushing on this pump. This force is pushing this way, so you get a reaction this way, and then that in turn is pushing on the vacuum chamber. Now, chances are that force isn't going to be very large, and the weight of the container is enough to create friction between the ground, which I have here by these dashed lines. This is typically how we sketch ground in structural engineering. You'll have the weight of the container multiplied by a friction coefficient will give you a resulting force of friction here, which will resist that force and keep it from moving. Okay, so just keep that in mind. So this is why I don't think we can even really, this would be so hard to time and do, and we're essentially defeating the purpose of the propellant by sucking it out as it's sprayed out of the CO2 cartridge. But the point of doing this episode is to show that when the CO2 leaves the cartridge in space, or what it would be compressed oxygen, but this is a pretty good representation of how those little jets work. When the oxygen is sprayed out into space, it just expands with space. There's nothing to push back. Whereas if you didn't have this pump on, as I've got shown here, you don't have the pump on, then the container fills with the CO2 propellant, and it becomes pressurized again, and so that would affect this. It would create a reaction, and you would probably see the CO2 cartridge move. So just wanted to go over that real quick and explain why I said space sucks and why it wouldn't suck in a container unless we had the pump turned on. So thought I'd make this short video and to continue thinking about the action-reaction process. I'm planning to do another sub-video, 5.2, in which I want to use a spring in lieu of the compressed gas to simplify things and to show why I don't think conservation of momentum would work, or using that principle would show that the gas could propel the spacecraft, because it's really based on, the conservation of momentum is really based on Newton's third law. So until next time, we'll keep looking at this problem and get into some different stuff with episode 6. So see you then. Peace.
Hi, I'm Brian Mon. This is Balls Out Physics, Episode 6, Perspective. This is one of the biggest arguments in the flat Earth versus spherical Earth debate, and it really is all about how we see, or how we perceive our world, the world around us. As I got into this debate over a year ago, a lot of people would say things like, "Why can't I see Mount Everest from California? Without an Earth's curve, I should be able to do that. Why can't I see the Statue of Liberty from the United Kingdom?" Things like that. And people would say there's a curve blocking our view, that's why we can't see those things. But that's not really the case, because we can't see things infinitely far away. And to show an example of this, just take this eraser. This eraser is about 1.5 inches by 3.5 inches. And as I move it away from the camera, you'll see that it gets smaller and smaller and smaller. And eventually it would get so small that it would just disappear from your view. You wouldn't need a curve or something to block it from your view to not be able to see it anymore. And that's how perspective somewhat works when it comes to objects. In the scientific world, engineering world, we don't really talk about how our vision works very much. At least I never did. And I never really thought about it until I got into this debate. And we're born into this world, and we start looking around, start seeing things. It becomes pretty obvious to us how our vision works. It's kind of self-explanatory, really. And we never need a tutorial. It's just, something's close to your eyes. You know it's close, far away. You flinch when things get close to you that look like they could hurt you. It's pretty obvious. But artists, on the other hand, they do talk about perspective, because when drawing three-dimensional scenes in 2 dimensions, perspective is a big deal. And so my fiance let me borrow this children's art book, and here in lesson 77, they've got this shown here in figure B here. They're trying to illustrate how to draw this old western town. It's shown up all right. How to make the buildings look like they run alongside a road off into the distance out here to the vanishing point. Okay, you can see the horizon's out here, all flat, of course, but that's just how it's drawn. And so perspective has a lot to do with how we perceive this world. And one of the best ways to start visualizing that is to think of looking down a long hallway, or look at a picture of a long hallway, or looking down a long hallway. You'll notice right away that the floor and the ceiling appear to be sloping toward each other, or the floor appears to be sloping up, the ceiling appears to be sloping down, and the walls appear to be sloping toward each other. Now we know the walls are plumb, and the ceiling and the floor are level, or they should be, and yet they all appear to slope towards the center point at the end of the hallway, however long the hallway is. And the corners also appear to follow this apparent slope towards the end of the hallway, but they don't. And something else to think about is that if you look down a long hallway and you crouch and then stand up, and crouch and then stand up, you'll start to notice that the floor in the hallway, the apparent slope of the floor in the hallway, decreases as you crouch and increases as you stand up. And the opposite is true for the ceiling. The ceiling, the apparent slope of the ceiling downward, tends to increase as you crouch and decrease as you stand up. The floor appears to slope up, the ceiling appears to slope down. I think that's very important when it comes to the flat Earth debate, because this is how the ocean looks over as it approaches the horizon. When you stand on the beach, for example, and look at the ocean, look out over the ocean, you see the ocean appear to slope up towards the horizon. Another thing to notice on the beach is if there's clouds out and you see birds flying around, if you really think about it, in your view, birds that are close to you actually appear to be above clouds. But just because you know how your vision and perspective works, that the birds are actually closer to the earth than the clouds are, but you still tend to see that. Very interesting to talk about how our vision works. It's pretty remarkable, and I think we take it for granted. And so another thing that's argued in I guess this falls into perspective, is a lot of people say we know the Earth is a globe because when you go up in elevation you can see farther, and people claim that that's because we're able to see over the curve. But I think that while that may be true on the globe model, it's also true on a flat Earth model. And that's because of that apparent increase in slope of the floor or the Earth. So assuming the Earth is flat, if you take this level, okay, and I hold this level to you, and try to keep it as level as I can. And look at the bubble, and I move it down. You can see more of the level as it moves down and up. You can see more of the ruler marks on it, and less as it goes up and down. And so on a flat Earth, you'd still be able to see more by going up in the air. So it's not a valid argument to say that the Earth is a globe because of this. I think on both models you'd be able to see farther as you go up in elevation. I think this is a pretty good proof of it. So a few days ago, I was sent a message by someone who has been questioning the heliocentric globe model, and he's what I like to call a closet flat Earth researcher. He's got a technical background, and he basically sent me a message because he's got nobody else to talk to about this because it's taboo to question our world. But he sent me a video. He said he's really doubting the globe model, but the video he sent me was by a YouTube researcher named Red Pill World, and Red Pill World has been using a theodolite, a surveying instrument, to measure angles over long distances and compare that to the angles you would expect to get on a spherical Earth versus a flat Earth. And in one of his videos, he did an experiment between Warren Dunes Park in Michigan and Chicago, basically using the theodolite to measure angles across Lake Michigan, angles from the horizon, from level view to the top of the Sears Tower, or a couple points on the Sears Tower, and the base of the Sears Tower. This is a really good video to analyze in this perspective video, because I think Red Pill World did a really good job. He said he's not a surveyor, but his calculations were pretty good. I spent a whole day going through all the calcs and just thinking about what he had done, and he concluded that the Earth is a sphere, but I don't think he accounted for the sloping effect that you would have on a flat Earth due to perspective. And a theodolite does work off of sight. You have to look through the crosshairs in the theodolite to use it. It's also another instrument used in surveying is called a sight level. It works the same way. It's kind of like the scope on a gun or anything that you look through that has a crosshair. The user, the person's vision has to be used for the device to work. And we all are subject to this law of perspective, this way we see, so it can affect what we're doing. And now typically, survey sight levels are accurate up to about 150 meters. I did a little research on it. I posted an article about this in the link below, and or in the description below. And so 150 meters is about 500 feet. And theodolites, I think that the maximum range I saw was about 1,000 meters, which is a kilometer, and that's less than a mile. And the distance from Warren Dunes Park to Chicago is about 53 miles. However, I still think the experiment's good. I don't think we should just throw it out because these devices aren't supposed to be used at those great of distances. For real professional surveying applications, of course, they can't use it. I mean, no surveyor would use it for this. But this is just an experiment to see what happened. And so you might want to watch this video. I post the link in the description. Before going any further with this, I'm going to go over some of the basics in this. I may put some clips here and there, but so you may want to pause and then go from there. Alright, so assuming you watched the video. In the video, Red Pill World did calculations for both a flat and spherical Earth. And so if we assume, without the effects of the sloping effects of perspective on a flat surface of the Earth, of the upward sloping effect, this expected drawing up here is what you would think you would see. So if we have the theodolite over here at 778 feet above mean sea level, and the Sears Tower over here 52.3 miles away and the top of the tower is at roughly 2,050 feet above mean sea level, then you should be able to just use a simple right triangle to determine what angle you should measure with the theodolite to the top of the tower. The angle you should have the angle you should the theodolite should calculate from having to rotate the device up from perfectly level view, assuming that this, perfectly level view from the theodolite right here, what angle would be measured by the theodolite here, as shown. So this is simple trigonometry. Okay, you've got 52.3 miles, which is 276,189 feet. That's your adjacent leg for your right triangle, and then your opposite leg. Okay, this would be the hypotenuse, the sight line. The opposite leg is 2,050 feet minus 778 feet gives you your opposite. So your opposite leg, the inverse tangent of your opposite leg divided by your adjacent leg gives you this angle, which is 0 degrees, 15 minutes, and 47 seconds. Okay? And surveying, angles are typically given in terms of an hour, for precision, that's what the devices give. If you want to convert that into a decimal angle, something that you can you may be more familiar with if you've never done any surveying or worked with this, you can just say 0 plus 15 divided by 60 plus 47 divided by 3600. That gives you 0.263 degrees. Very small angle, okay? Very small angle up. That's what you should expect to see. But that doesn't account for all of the sloping effects due to our perspective, due to the user's, Red Pill World's perspective, due to his eye. And so this is what you would think about if we were looking at this. If we could see the Sears Tower and the theodolite, we would expect to see this. If we were at a distance perfectly perpendicular to his sight line.